Hello everyone that's just joined us, and welcome back to the second session of our workshop on object tracking and its many guises. Today, in the second session, I'm going to start by having a little discussion on metrics for multi-object tracking, which is very interesting for the topic of this talk. And then we're going to have a bunch of invited speakers. We're going to have Angjoo Kanazawa, Deva Ramanan, and Girshick. And in the middle there, we're going to have a very exciting roundtable discussion with a bunch of our speakers discussing interesting things to do with object tracking. So as always, see the website for an up-to-date schedule. So I'm going to give a little brief talk on the state of multi-object tracking evaluation. So the most commonly used metric, it's not used in the workshop for this benchmark, but it's used in many other benchmarks, is MOTA. Now in MOTA, it's calculated by bijectively matching ground truth and predicted detections together, and then counting the number of ID switches that occur. So these ID switches occur when the ID for a predicted track switches relative to the correct ID for the ground truth track. So then the final MOTA score is simply 1 minus the sum of the detection errors plus these ID switch errors. And this ends up being heavily biased towards detection because the number of ID switches is usually about 100 times less than the number of detection errors, so false positives or false negatives. So this is heavily biased towards detection, and this also is only able to evaluate short-term tracking because if a tracker corrects itself, so if it makes a mistake and then goes back to the correct track, this will be counted as 2 ID switches and 2 errors. So it isn't able to correctly evaluate long-term association over time. So there are other tracking metric alternatives, and one of these is IDF1. So IDF1 operates a little bit differently in that instead of matching detections, whole trajectories are matched. So whole trajectories are bijectively matched. So the best matching trajectories are matched together. And any trajectories that are not matched in this best matching, as well as any detections of the best matched trajectories that are not that aren't matching, are counted as errors. And the precision and recall can be calculated with respect to these errors, and IDF1 becomes the harmonic mean of this precision and recall. So this, unlike MOTA, it's actually the opposite. It actually ends up being heavily biased towards measuring association. And this is because it isn't even monotonic in detection. In IDF1, when adding in correct detections, correct tracks, if they're not ending up being matched to a ground truth track because another track already is, these will actually count as negatives and decrease the score, even though you're adding incorrect detections. So in the end of the day, IDF1 ends up being more about estimating the correct number of ground truth tracks with your projected tracks, so estimating the correct number, rather than actually measuring detection and association respectively. So we'll move on to a third metric, which is getting more use recently. So it's been used here in the TAO challenge, is this track MAP metric. And this operates a little bit differently than the previous 2 metrics. So in this case, the trackers are not required to output the final tracking results, but rather confidence scored potential tracks. Like IDF1, whole trajectories are matched between the predictions and ground truth, except in this case, the highest confidence trajectory, which is above a 3D IOU threshold with a ground truth trajectory, is that's matched. So after calculating the trajectories that are matched, the precision and recall can be calculated over a range of different confidence thresholds. So we can decrease the confidence, and for every trajectory higher than that confidence, we can calculate the recall and precision. And the final track MAP score is equal to the area under this precision recall curve. So this metric also has a bunch of problems. So the first is that the different error types are mixed, such that one cannot tell if an error, because the tracker didn't output a track higher than the 3D IOU threshold, was caused by detection, association, or localization. All 3 types of error would have been contributing towards this thing not meeting the threshold. Secondly, if a tracker improves a trajectory from a 1% match to a 49% match, this won't show up in the final score because the overlap needs to be higher than quite a high threshold. Thirdly, by adding in a 49% correct match, this actually will decrease the score. Even though you've added in something that's correct, 49% correct, the score will decrease because this will count as a negative. This is the same as an IDF1. So again, track MAP is non-monotonic in detection. And finally, because track MAP operates on these confidence score tracks, potential tracks rather than final tracks, it potentially can be gained by adding in many low confidence tracks that could overlap with ground truth tracks just by chance, for example. So we've gone through the 3 most commonly used metrics and identified a number of problems. So what about a potential solution? So recently, myself and some colleagues of mine have been working on a tracking metric that we call HOTA, so higher order tracking accuracy. So like in motor, matching is determined at a detection level between predicted and ground truth detections. And then once we have these matches, we then explicitly measure a detection and association score separately. So the detection score, as you can see on the right, is simply a Jaccard index over the correct and incorrect detections. And the association score is what's novel here, is that we're able to, the association score is calculated by, for every single detection match, so every single true positive, this match between this ground truth detection and this predicted detection, each of these belong to a trajectory. So we measure the alignment between the ground truth and predicted trajectories for every true positive match. And to get association score, we average those alignments over all the true positives. Then the final HOTA score is simply the geometric mean of this detection and association score. So this is able to measure long-term tracking because the association score, this alignment, is able to measure long-term alignment over trajectories. And this explicitly evenly weights detection and association. This fixes a lot of problems of the previous metrics. So let's have a look at how this works in practice. So here I have a very simple tracking problem. So we have a ground truth track present in 100% of the frames. Three tracking results that we're going to compare. So as we increase from A to C, the detection results of the tracks get better, as you can see, and yet the association gets worse. So although we're getting better detection as we go down, the track's getting more split up and getting worse association. So let's see how the different metrics operate on this. So let's start with motor. So motor, as you can see in the second column of metrics there, is highly correlated with detection. Basically, the effect of each ID switch is negligible compared to the effect of wrong detections, as we discussed before. So motor highly correlates to measuring detection. IDF1, on the other hand, is the opposite, highly correlates to measuring association. And actually, as you can see, as the detection gets better, the score goes down. So this is because as it splits up, as the tracks split up, it produces more and more negative predictions because only one trajectory can match the ground truth trajectory. Track MAP, I didn't put in the table, but I put it at the bottom. Actually, in all real tracking cases, it's going to give you 0% score for all of these because it requires at least a 50% threshold for matching. So B and C are automatically out. A could match if all of the detections have 100% localization accuracy, at least in the definition used by the tail metric here, which is really ever the case. And if they do, then you'd get 100% match. You'd have a jump from 0 to 100%. Now let's look at how the HOTA metric actually operates here. So HOTA is composed of the detection score, as you can see on the left, and the association score on the right. So the detection score is very simply the percentage of correct detection. So as you can see going down, it's 50%, 60%, and 100% correct detections. And the association score is the average alignment over the trajectory. So as you can see, going from A to C, 50% average alignment, 35% average alignment, and 25% average alignment. And then the final HOTA score is the average of these. So we've chosen the examples in A, B, and C carefully, such that as detection increases and association decreases, these decrease in a similar way, such that for these 3 examples, HOTA gives a similar score. So basically, that is all I have to say today. I'll leave that for you to have a look at. So basically, that's a discussion of the state of multi-object tracking evaluation and the number of solutions in the current metrics and our proposed solution. So this work isn't currently online, but it will be soon. So hoping to share it with you all soon.
Cool. I'll just jump in here. Thanks for the talk, Jonathan. I think this is a really interesting problem, and like I think metrics and tracking have been a huge source of issue, and even in Tao we kind of struggled to figure out what metric to use. That was in the pre-HOTA time. I think it's I wish we had more of these discussions, especially the fact that MOTA is almost primarily measuring detection is, I think, kind of surprising to people who haven't worked on tracking before, or at least it was to me before I worked on tracking. I think I'll hand it over to Pavel, who I think is going to introduce the next speaker.
Yes, thank you, Axel. Thank you, Jonathan. We're finally going to start our invited talks in the second session, and I'm happy to introduce our first speaker, Angjoo Kanazawa. She's a professor at Berkeley, and she was before a postdoc at Berkeley as well, and she did a PhD at UMD in Maryland. But she's, of course, mainly famous for her work on reconstructing human and objects 3D shapes from images and videos. And in our context, I think it's very relevant because for tracking now, we have two types of approaches, right? Ones are just primarily appearance-based, and they don't really visualize 3D information visibly, or the ones which take 3D information as input in form of LiDAR sensors. But of course, we would be all interested to know whether we can actually predict 3D randomness of objects during tracking and then utilize this information somehow. So we're all curious to know what Angjoo thinks about it, and if she thinks it's useful, does she think is the best way to go about obtaining such information. So I'll pass it to Angjoo at this point.
Here we go. All right, thank you so much for the introduction. Can you see my screen?
Yes, but it seems we're seeing kind of like, oh, okay, now we see it perfectly. Yes.
Okay, great. All right, thank you so much for your introduction. I'm excited to speak here, really, yeah. So today, today I am talking about challenges in perceiving 3D humans from video, but really question is like, how can tracking can help in this direction? And it's something that maybe we don't always talk about when we talk to the 3D people audience. So this is why I'm really excited to talk about this. And in particular, I think I'm going to talk about this particular effort that we tried to use 3D to improve tracking and failed. And so I'm really excited to talk about it, and hopefully maybe people can take it somewhere more. All right. Okay. So to set the tone, I think a lot of my research is really coming from this premise that we live in a world that is 3D and dynamic, full of humans and objects and animals interacting with each other. And we have these videos and images of these things, and we really want to understand their underlying states in 3D, because that's the kind of world that we live in. So this is why a lot of my work and my lab's work now have been focusing on recovering non-rigid 3D objects of humans and animals and other object types too. But today, I want to talk about, in particular, this direction of 3D human motion. I'm going to give a real quick basic on like how these methods work and the applications which they can be used for. And then in all of these, it's not really as emphasized, but whenever we do something with the human motion right now, tracking is really essential. So I will try to highlight a little bit more of that. But once you get this background knowledge, I will discuss what is the challenge right now, and actually, if tracking could do, how can tracking improve our direction in this area, which really needs some work. And is there any way 3D can actually help the tracking? And we had an idea that we tried that didn't really work out, which I'm excited to talk about, so that perhaps more things can come from that kind of direction. Okay. All right, so I'm gonna do a 3D human mesh recovery crash course in case you weren't familiar with this direction. So let's just go through this in like 10-15 minutes. Okay, so this is a really challenging problem. One of the real challenges is that there's this inherent ambiguity. So you have these 2D point joints detected on the humans, and actually in 3D there are multiple interpretations or multiple 3D states that would explain this 2D joint. So for example, one interaction is as we expect things to be. Oh, by the way, if you have any questions, you can feel free to ask me quick questions. And also, please let me know if my video is not playing or if my audio is too loud or not too loud. and things like this. Okay, great. All right, so that's one interpretation. But the other interpretation is something like this, where the knee is completely bent in the rear direction. And clearly that's not the right interpretation of this person. We know this, but they both equally explain the 2D joints. So this is really how 2D joints alone is not enough to explain the state of the people. Now we know that this is the right one because we know a lot about our body and we have our prior knowledge that our knees don't bend like this. Right. So in order to resolve this kind of ambiguity, what we use is this prior on what human body is like. And using that, looking at this picture, you can guess that even though, you can't see the other side of the skater in this particular video. Oh, no. I mean, don't tell me that the videos are not playing. Okay, I don't think the videos are playing, which is seriously detrimental for this particular work. I'm just going to restart. Sorry for this technical issues. I think I just need to restart my PowerPoint. So I'm doing that right now. Okay. If it's a video-based talk and if the videos don't play, it's not very good. Let's see. All right. Okay. Meanwhile, as it's coming, another thing that I would like to notice is that I'm not also an expert in tracking. I mean, there might be information that I'm missing, and there might be something like, oh, actually you can do this in tracking right now, or these are different ways you could go. And so that's something I would really love to know, and this is why I'm really excited that I'm speaking here. All right, so my PowerPoint is back, and so I'm sharing my screen. Okay, so now we're back, and let's really hope this video plays, and if it doesn't play, okay, yay! All right, video plays, okay. All right, so where does this prior knowledge of the human body come from? How can we gain this? For humans, we have a lot of data because people are really cooperative. We can ask people to go into the lab, we can scan them. So we have lots of data. And groups like Michael Black's lab at MPI have made this really very nice morphable model of human bodies that a lot of these works now use. And so let me explain how this works. So quickly, the way we represent human body, we factorize the shape variations into shape, intrinsic shape, and pose. So the shape or an intrinsic shape is how tall you are, what are your joint proportions. And these are things that are captured in like a PCA, like low dimensional space with a very fixed pose. So there's no articulation in a fixed T pose. This is 10 dimensions. You can turn this around and make the person tall or short. And then there's also this kinematic tree of 23 joints, which is specified with joint angles in each joints to specify how they're bent, and this is the articulation. When you join them together, you can use this graphics techniques called linear blend skinning to deform the surface of the shape according to the articulation, and then you can actually model any kind of approximated body and the shape of a person. We're always taking a picture, so let's also throw in like the 6 degree of freedom camera over there also. But then when you add all of these parameters, it's really just 85 numbers. Okay, so the first is like knowledge on what human body shape is like and what human kinematic structure is like. And when you combine the numbers, it's really 85 numbers that defines the body in the image. And so $1 million question is, how do you recover this 85 numbers for every single one of you from a single image? And so in 2016, with Federica and MPI colleagues, we developed this approach that was fully automatic approach that tried to reconstruct humans from images. For this approach, what we did was to extract 2D joints from images and then solve for pose and shape that explain such 2D key points. And by solving, what I mean is that I'm going to optimize this objective function where the idea is you want to minimize, you want to get the 3D such that when you take a picture, the 3D joints fall onto the 2D joints. So now I'm going to play a video where this is the initialization of the person in the middle, and then the person is going to start, moving around during the optimization as you search for this. And of course, there's a lot of priors that I'm not going to talk about over here, but we incorporated it in order to solve this problem. And there has been many, past instances of this kind of work, and because thanks to the developments in 2D joint detection and some of the priors, we were able to do this in a fully automatic way. But this is an optimization-based strategy. So what happens is that it's not really looking at the image, and it's just looking at 2D joints, and it's also quite slow. So now next question is, why can't we just throw a deep network at this? It's like image in and 85 numbers out, right? Like how difficult can this be? Well, it turns out this 85 dimension is a very high dimensional space. It's rotation is difficult to regress. But more than anything, you really don't have any like data. So that's a real challenge too. There's no ground truth 3D data for images in the wild, because in order to get that, you have to put them in a motion capture studio. So then it really calls for some kind of weakly supervised approach. So the challenges are that there's multiple, solutions that explain the same 2D observations, and that there's no data. That we have these motion capture data, which has some ground truth, which is great, but only for green screens, and they're not real image statistics. And so for real images like Coco, you don't have the ground truth 3D. And when you only train on images that have green screen backgrounds, these approaches don't generalize to the challenges in the world. Okay, so those are the two challenges. And so the solution that we had was to really constrain this idea. And the key idea was that even though we don't have paired 2D to 3D labels, we have a lot of unpaired labels. So by that, I mean there's lots of these 2D images. There's no ground truth 3D for this. But separately, we've collected a lot of people in the 3D. And so we have lots of ideas about what the pose space could be. So let's have a network explain what the 2D joints are, but while staying within the distribution of these real 3D joints, okay? So that's really an instantiation of the idea that was in human image recovery. We have an image that outputs network that outputs 85 numbers. And if you had ground truth, you could just do supervision on this, but often you don't. So you will do, again, with this 2D reprojection thing, like please explain the 2D joints using this 3D in the camera. So you can train on all the Coco images, which is fantastic. But again, of course, due to the ambiguity, if you just did this, you're going to get all these monsters. So you want to make sure that the space of the poses that it gets outputted is on the manifold of possible human poses. And then we set up an adversarial prior like this with a discriminator to do this. And then more recently, this kind of idea has been also used for video. Anyway, so I just want to give a very quick overview. So, okay, that allows you to recover these humans in this like cluttered environment. And I really have this I really like this latest work called Spin from Michael and Kostas and Nikos and George's work. So the idea is you have an image and you predict this person like the way I just talked about with an HMR, like a single shot 3D reconstruction approach. But then you can actually take this as an initialization to the optimization based approach that I talked about first of all in the first place, and then improve the prediction. Now this optimized shape or the parameters can actually serve as the ground truth for the network that was trying to do the prediction. Now, so this is yet another way to go around lack of supervision. So you do optimization, use the output of the optimization as a target for your regression network. And this works really well because if it's supervised, the networks can converge a lot faster. So I really like this approach. I really think it unifies the optimization and regression in both many ways. And I think this kind of idea is also useful in domains other than 3D humans. But okay, so you can do this and then you run this, but then you run it on a per frame images and it's not that smooth. So we really want to incorporate some motion prior. So that's where really the tracking comes in. How can we incorporate the prior of the time? Okay, so just as a quick recap, we did this optimization and we also did this one-shot inference. And like you just saw in Spin, these are not like orthogonal approaches, they're complementary. Like you can always take a prediction and refine it over time with smoothness. And so we've tried this approach also, but it's somewhat, if you just did post optimization to make it smooth, it's a little bit unsatisfying. There's a lot of temporal information in the data. So how can we actually have a network that incorporates the temporal information in the video frames? So that was one of the approaches that we explored last CVPR. And so this is human mesh and motion recovery. So the idea really is simple. You have these images or frames from the video, and then you run the same convolutional neural network that outputs, the human pose, pre-trained from the previous task. Now, instead of actually directly asking for the 3D pose and shape for each frames, we actually keep them as some latent representation, like right after ResNet. And then you actually do another 1D temporal convolution over time to aggregate such latent features with with another convolution where this big yellow thing is, say, like a movie strip representation of the video. And then from here, you can actually ask what the pose is. And so then this network is able to actually take account of the temporal context. And to encourage them to do so more, we ask the network to also predict the previous and slightly future human poses, which helps it take more attention to the temporal information. And you can train this with exactly the same law. So this is why I wanted to kind of talk about how it's being done. Okay, so when it comes to tracking, so this is actually where I don't usually talk about this, but where does this movie strip really comes from? This actually comes on human tracklets. So during training, we run all the tracking in these videos and then make them into tracklets and then use them as our supervision. So you can see how, tracking is really essential here. Okay, so here are some results where you just run it in a single frame, which can be kind of not temporally consistent. But once you have a model that can look at this perspective, then it actually gets a little more smooth. Okay. So another challenge in video is that there's really not that much data. The data with ground truth 3D is really small. And then our approach can be trained on data with just 2D key points, so that's much better. But even then, there's actually not that many minutes of data with 2D key points annotated because it takes a lot of time. Okay, so what we did here was the problem with the video is that the labeled data is really limited. But there's plenty of unlabeled videos. There's 300 hours per minute uploaded to YouTube and probably a lot more now. So how can we, take advantage, embrace the power of YouTube and Instagram in order to train these approaches? So what we did was use the off-the-shelf 2D joint detection as a pseudo ground truth 2D. So what we did was take these YouTube video data sets and then run open pose on every single frame. Maybe we should have run a tracking based approach, but this one was per frame. And then collect more data. And then we also went to Instagram and then just got a lot of video data and then run humans. Actually, also we were using tracking because in order to figure out, which videos to use, we had to use tracking to identify interesting videos where humans were trackable, right? So this is also, where quality of the tracking directly matters in the quality of our data. But anyway, this approach allows us to mine lots and lots of minutes of people moving around in a realistic scenario. And then you can train on this data. And what so happens is that the more you use pseudo labels or real data with, even though the 2D labels are actually not very, can be quite noisy, having that information still really improves can improve the detection. And for time, there's some analysis that really shows that methods, algorithms that can look at the temporal context will take advantage of this massive amount of data more. So the pseudo training works a lot more if you treat them as video instead of single images. But in context of time, I'm just going to skip all of these approaches. And I do want to show this results because this is a result from two methods, single frame versus in the temporal context. And single frame actually looks really good over here. But when you look at it from a different viewpoint, you can now tell that they're really unstable. So whenever you're doing something with 3D, you really need to look at a different perspective, different viewpoint. Otherwise, there's no way. I mean, obviously the fits, tell you something, but it's very important that you look at this. Anyway, so the code and data is available on GitHub. And there's a recent approach from Michael Black's lab, which is called Vibe, which extends this idea, and then it's the state-of-the-art approach, and also uses this idea of motion discriminator. Okay, now I think I have 14 minutes or so, and I want to get to an interesting part. So let me just show you quick applications without really talking about it. How to do it. So the benefit of video is that the future is in your hands. So now that you have a video, you can actually take this particular frame and be like, what is this person going to do in a little bit future, and ask these interesting questions, which could lead to questions like, how do you understand what the intention of people are from video and such. So in ECCV, Jason and Pana and with Mike, with Jitendra, we took the output of previous approach to train an autoregressive approach that, given some video, can predict what the future is going to do. And really, it's a simple approach that takes the previous takes like the previous approach on human mesh motion recovery, but makes these temporal convolution into a causal temporal convolution. So it only looks at the past. And we really do something like a sequence to sequence based approach. You take the current observation, you predict what the next thing is going to be, and then you just feed it in as your next input, and you just repeat this. We do this in the latent space instead of the pose space, and then you can read them out. So that can give you these results like given some video that's conditioning, and now it can predict what the people might going to do. Okay, another interesting direction is that once you have video, you can do these kind of things where you go take a step towards this baby in terms of visual imitation learning. So this baby is watching this video, and clearly it's a movie, so you don't know the 3D, you don't see the 3D, it's a 2D flat screen, but the baby is clearly interpreting the 3D motion that is happening behind this. And so how can we, get to there? And this is more like a control problem. It's not just about understanding what the joint angles are from the images, but it's also about learning to actuate your muscle or control system in order to execute these actions. And so prior work uses motion capture to study this problem. So the idea is you want to manipulate this character in simulation, and you only have reference motion. You don't know how they actually actuated their muscle or torques and stuff like this. So you need actions to move this, but then you only have a recording of joint angles. So you can pose this as a reinforcement learning based approach and then train some policy that imitates the reference motion. Now, in this case, the reference motion comes from motion capture, but if we could get, 3D humans from video, then you can expand the world from video, and then you can do things like take this video, you recover 3D humans to it, and then you can use this as a target to train your policy. All right, and then, which you can do because now it's not just playing those joint angles, but you can actually interact with them and do all these cool animation tasks. All right. But I do want to get to some interesting questions, so let's just go for that. So those are like stuff you can do, these applications. All right, so here are some reflectives. So real challenge in video for 3D humans, aside from the usual things like computation and the lack of labels, which we try to address through the pseudo ground truth, is really, for me, obtaining a long tracklet of people, okay? And this is because not that many people do interesting things in front of the camera without getting out of it or with a full body. So then, okay, so this is a fantastic YouTube channel. It's a great video source. It's really fun. And so sometimes you can get this unique data where the person is doing something in front of the camera in an interesting way. It's totally staged, okay? And in real life, there's a lot of other challenges, right? Such as shot changes in movies or media. You see Motopo-san, there's a big change. And of course, there's lots of occlusion and approaching towards the kind of videos and the images that you look in tracking, I think. So why do you really need long video tracklets? Well, one thing is that in successful sequence-to-sequence models like NLP and speech, the data is really, really long. This allows you to train your autoregressive models many, many times, which is required in order for making these approaches more robust. Another thing is really there's more interesting human behaviors. If you only focus on videos where people are doing something, then you can do these batting or these, dynamic motions, but if we want to get to more interesting behaviors and how people interact with each other. So really my wish is I want the trackings to work so that we can get really long tracklets that are robust to occlusion. And you can connect it, so it's connecting re-ID. So I think this theme of this workshop is fantastic. But let's just look at one challenge, right? One challenge is human-to-human occlusion. And this is a real challenging problem because the occluder looks like something you're supposed to be able to detect, And so here are some images. And the question is how can 3D cues help in order to identify these things? So here's the idea that I pitched to a student. Okay, so in 2D, occlusion is hard because you have two people walking, and especially if the appearance is ambiguous, when they overlap each other, they completely, it's difficult to disambiguate this, okay? And so this is a blue person and an orange person walking by, but then, they overlap, and I'm sure there's other sophisticated way, but making it really simple, you may confuse their identities because they just overlapped, and from 2D images, it's difficult to disambiguate. Okay, but in 3D, in 2D they overlap, in 3D they actually don't. So let's take that same picture, but look at it in a 3D viewpoint from the top down. It's two people walking that way, but in this case, you actually have a Z, and then you know that people are not going to teleport from one depth to another. So you actually, they aren't overlapping. And then, you can disambiguate. So this is really the core of the idea, which is that from these images, can you recover their depth and use that as an additional metric in the similarity during tracking to identify whether these people have enough overlap or not, and to do the association. So the brave student, Edward. So I was like, my student Edward, like, I have this idea. I think it works. I think it's and I'm sure people in 70s have thought about this idea, but like maybe it's a good time to revisit, because 3D human wasn't really working in videos in the wild. So like if you had 3D data, you could try this out, but now we can actually see if it works in real life. So brave Edward went in there and got these tracking data sets, and we got this detection in the 2D box. And the formulation of this idea is that we will use the state-of-the-art human mesh recovery methods like spin in order to get the humans. And then, so I'm skipping on some details, but these human mesh recoveries are often in the local coordinate space. So absolute depth is difficult to identify. We actually have a paper at ECCV touching upon this, but you can use the similarity triangle or a simple 3D trick to approximate their depth. Now that you have their depth in 3D, so now you have their Z's, now you can draw a 3D bounding box on top of the people and use this as an association term. Like, are they actually overlapping in 3D also and not just 2D? And then use this as an additional metric and send it to some kind of tracking algorithm to associate this. Okay, so that was the idea. But the problem was, what happened was, the idea was promising if the 3D reconstruction was good. So on a video like this, spin gave us reasonable results, and we could use this kind of idea. However, in these cases, the simple tracking baseline also worked, and it might have been different if these two individuals kind of crossed over, so I was like, okay, well then let's look at more challenging cases. And then what happened was that like, when occlusion is severe, which really tends to happen in your tracking type data sets, 3D is not going to be very good, because you only see a sliver of these people. And so it tries to do things, but it's not, there's going to be lots of noise, and because of this, you have issues in the Z association of this. So therefore, you couldn't really use their 3D box more reliably. And so really, like, the thing is that the tracking setup is real intense, which is a great thing. Which, like, for example, here's another kind of, images that we don't really deal with, is unusual viewpoints. And so, mesh recovery approaches suffer from these uncommon view angles. And like, I think this is fantastic. It really just shows the kind of challenges, like the approaches in 3D human mesh recovery has really improved a lot in the last few years. But there's still lots of challenges. Really in the wild kind of data is in the tracking sense, which really kind of shows lots of work to be done in this field, and that's exciting. And then, although I think one point is that in order to really explore this better, I think the tracking is really difficult, and there's other kind of intermediate spot where it's like, maybe people dancing, like there's overlaps so that you can study this kind of setup, but not as really crowded, and not really like clean like 3D human. So like, one reason why we didn't really pursue this approach was because it's not going to work for really hard tracking data. We can set up something new for, like, for example, there's a new very good data set from Gerard Ponsmal's lab called 3DPW, 3D People in the Wild, which uses like IMUs to have ground truth in the wild, and like tubing game people walking around. But like two people set up, and there's some occlusions there, so we can kind of explore in that domain, but then it's not going to be appreciated as a tracking paper. So it was kind of somewhere in between. This is one reason why we didn't really pursue this, but I think it's, I think it certainly is worth pushing a little bit more, but it also highlights, like, work that needs to be done in the 3D human world. and hopefully this inspires some brave. Maybe I didn't know so much about what's going in tracking, so if you know more, maybe you might have like the data sets or situations where you could head, and I would be really happy if somebody worked on this, because I really want long tracklets, and you know, please work on this, or like, yeah, I'm happy to discuss about this in future. So that's really, you know, some of the lessons and reflections that we learned from this. But there's some hope, or like, I think, directions. So in this ECCV, there's a cool new paper from David Fui's lab with Chris Rockwell and David Fui, where they suggest a simple but really effective approach to make approaches like HMR more robust to occluded people. It's like I think this is like a 20% human problem, where you only see 10% or 20% of the body part of the human. Can you still kind of predict their 3D in a reasonable way? And so this is super exciting. I'll be going to this poster session. I recommend others who are interested in this domain to also do so. So yeah, this is a very good direction. And here's some shameless plug, which is that at this ECCV, we have two works. So one is this humans plus objects in the wild. So we focus a lot on humans, but you know, the world is not just humans. There's other environment and objects. So how can we recover humans and objects in conjunction? And this really actually talks about how to situate people in the 3D. So this seems obvious to you, but a lot of intermediate solutions happen, like where the people are floating in the middle of the air. So we kind of give an approach to do this. And there's another paper from Shubham and Jitendra, which is doing 3D without key points. And so this is more in the direction of how can we learn more about unsupervised, how can we learn more about 3D shapes in an unsupervised manner? And we get to learn some morphological models where like there's, you know, deformations like we did for human bodies, like the PCA stuff. But we want to learn that from just images. Okay. Anyway, so that's that. Here are some poster numbers. I should have shown this earlier, but maybe, you know, if you're interested, you could take a screenshot and come say hi. I will be at the second sessions. Okay, so with that, I think I'm out of time. And okay, quick takeaway, which is that we need long tracklets that are robust through occlusions, viewpoints, and getting outside truncations. 3D can be useful, but occlusion is still a challenge. So we need to improve some of these approaches, and there are some promising directions like the one from Chris and David. I think there's also a need for a more variety of data sets that is something in between the tracking and the 3D human motion recovery. I think one is way too clean and one is way too hard. And I think we want to start somewhere in the middle, or I mean, at least that's the way I felt about this, and I'd like to learn more about this tracking. So I'm looking forward to watching other previous workshop talks later in tracking. But I think in all, there's a lot of really exciting new challenges, and there's so much things to be solved in this space. So that's that. And thank you for your attention. And I really want to thank my collaborators and students who really, without them, a lot of this work is not possible. All right. Thanks.
Yeah, thanks a lot, Angjoo. Thanks for a great talk. And I guess now we have the questions. Do we have any questions? Do we have like any questions in the chat? I don't see any, right? Yeah, then I'm gonna can ask myself maybe. So yeah, like, again, like amazing talk and a very interesting experience with using these 3D meshes for tracking. And I have to comment also, I love your wallpaper, but that's off the topic. On the topic of the tracking experiments, it was really exciting to see your struggles like with these data sets. And I mean, right, you're trying to solve this very hard task of human mesh reconstruction and to help solve this also very hard task of tracking, right? So I was thinking maybe if you could reduce, what do you think, if you could reduce the mesh reconstruction task to something simpler, something which doesn't require like, because you don't need all this detail, right? You only need like a subset of this information to actually help tracking. So have you thought maybe about doing some intermediate thing, not like a full mesh? And maybe that would be easier to make work in this challenging setting.
I see. Yeah, that's true. Like, yeah, it's true. Like, you know, you don't really need the surfaces in order to, you know, try out this idea, right? Like if you know their points. So I think, you know, there's two different approaches in 3D human pose. Like one really just reconstructs 3D joints, and one does this with the surfaces. I think the 3D based approach would have been interesting to explore. We didn't really try it in that those papers because yet another, I think, problem is that many human papers are not really designed necessarily for occlusion. So regardless of whether there's a surface or a 2D joint or 3D joints only, yeah, the training data there tends to be too clean that it still would have a problem. But it's something that we didn't really push into looking for too. So I think that's certainly like a direction, yeah, I would be interested in.
Yeah, thanks a lot.
But to add to that is another thing though is that when there's a severe occlusion, right? Like especially like there's like only see half of people are in these situations. I think the top-down knowledge of what people are like is actually really helpful. And so if you only see small area, I think local approaches alone might also have a problem. But it's certainly like a trade-off because yeah, there's a trade-off.
Yeah, for sure.
All right, I think there are a couple other questions, but we're running late, so maybe we'll start off the roundtable. Thanks again for the great talk, Angjoo. All right, so I'll start off the roundtable. So for the roundtable, we'll have Angjoo Kanazawa, Yuri Matas, Deva Ramanan, and Cordelia Schmid. And the format is basically we've written up some questions that we'll keep asking, but we really encourage people to ask questions in the Q&A as well, and we'll ask these to the speakers. So yeah, I guess I'll start with one purposefully vague kind of high-level question. So what we've all talked about a lot of kind of different challenges in tracking. Maybe one question is, if you had to pick one, what is an exciting challenge in tracking or an exciting application area for tracking that you're excited about for the next 5 years or so, that you think either a challenge that hasn't been looked at enough or an application that hasn't really been addressed by tracking?
I guess I could start, but I think that was really in my talk, I think it's really like long tracking, and I think video is really interesting, but video is only a small snippet of what's actually happening. And so we need to be able to, thread the needles or like connect all of these different observations. And I think that's where tracking could help long-term tracking. Yeah.
Maybe another comment I'll give is kind of the thinking about how to integrate tracking in 3D. I was struck by Yuri, the last video you gave in your talk of what the challenge video of a postdoc trying to, there was a 3D object that was hollow inside, trying to understand how it looked different from different viewpoints. So somehow, as you track, actually building 3D representations, which also ties into very much what Angjoo was saying. It feels like this is still open ground.
So my view is that there will not be a single grand challenge tracking problem, but I see convergence. So as I said, the SLAM people try to do reconstruction, so we'll try to, I think methods will converge. Some people will work on fast 3D reconstruction. The 3D reconstruction will connect to 6D pose estimation. And what we've seen is for one complicated articulated objects, which is the human, where we have lots of data and it's of extreme importance, someone chose a representation, it's very specific. And still, it's very difficult there. And to generalize this, to say, this is a general representation for modeling any articulated or non-rigid object, and this is what we should recover and track. If someone solves that, we'll have a very general sort of like SFM, motion segmentation, tracking with 6D pose estimation. This will be the mother of all things, yeah? The video that will provide data for everything else. Yeah?
Cordelia, can you hear us? I think you didn't have permission to turn on your video until just now, but hopefully I think you should be able to now.
Yeah, I'm good. I'm hearing you.
Oh,
So I guess for me, it's like there are many different challenges, right? I'm kind of what I gave in my talk. I'm interested in using it for video understanding, but I think what Andrew said is I think having this long-term tracks is exciting. I think there are a lot more challenges than people actually assume, right? Tracking in general, people think it's like a simple problem. You have a small box given, you want to track it for a while, and actually I think it's good to get away from this simplified representation or definition of tracking and see it more as extracting long-term identities over the video, right? And then it can be used for 3D or for something else, but it's kind of a building block for many things. And then obviously you could do it end to end, but initially, I guess we want to do it we just want to have some kind of consistency, right? Which is important.
Yes, thanks everyone for your question, for your answers. And right, I guess the idea is that we just ask questions one by one, right? Okay, so I guess I'll then go now with the next question. And it will be to Jury first, but then others maybe can add as well, I hope. So like I saw your talk, it was very interesting viewpoint on tracking. And in particular, you were making this like two distinctions, like of short-term and long-term tracking, which you think will converge, right? And then also tracking objects and regions, which you maybe don't think will converge. If I understood correctly. So I was thinking, can you then imagine actually something like long-term tracking of regions? Because I think to track something long-term, it has to be an object, right? If you want to re-identify something, then you cannot really do it with a non-object. So do you think then maybe that's the reason then why the object and stuff tracking cannot converge? Yeah, Jen, what do you think about these distinctions?
So okay, coming back, first thing, like convergence of multi-object tracking and single object tracking, I'm not so sure about it. But for instance, we had this talk about metrics, and I was thinking, why don't the multi-object tracking people just try to do the same metrics as simple object track, single object, and say average above over all objects? Yeah, that would be, to me, a baseline metric. So what is the long-term metric for a single object? Well, maybe the average overlap over the whole sequence. Now, so what is the difference? Why can't you do that? Well, because multi-object people sort of make excuses for swaps. So they say, if I lost the object and my tracker swapped, that's actually better than losing the object, but maybe it isn't. So maybe we can force these things to converge faster if we say multiple object tracker is not that different from many single object tracker. Now, coming back to these regions and objects, actually, I have been always working on this, what I call general tracking. And before deep learning methods, it was quite difficult to incorporate prior knowledge. So I think the main difference is that when we track known objects, we can rely very, very heavily on prior knowledge, and maybe tracking by detection will be a very strong competitor in all cases. And then we have things like, I'm working also on automotive projects and things like random objects thrown at cars, like parts of tires and things like that. And I think very often for very fast things, you recognize something is moving at you, you track and you avoid it before you recognize. So maybe short-term tracking will be always different of a region. That I think that maybe, I'm not a psychologist or psychophysicist, but I think that they say that before you recognize, you have to stabilize things on your retina. So you see something moving, maybe on the periphery of your vision, you focus it, you track it with your head, and when it stabilizes, then you only recognize. So maybe for regions and fast-moving things, you track before recognize. For slow things, you recognize and then you follow. Maybe we confuse the things that I recognize a bus and then I can follow it. I turn my head somewhere else and I re-recognize the bus, but that's a very different problem of avoiding a stone thrown at me. So maybe these are quite different things. Fast avoidance of something thrown at me and long-term following of objects from known categories. And maybe we mix these two things together. And that's why I think that maybe they should be separate. Yeah. So one thing has to be very fast. Maybe recognition by its nature is not something very, very fast in terms of sort of survival. So that's, maybe I've said enough, yeah, on this topic. It's a complicated topic. I'm not saying I know. These are just sort of random thoughts that came to my mind. Yeah, but actually long-term tracking when we started was on arbitrary regions. So it's about learning a detector, and we have this word pseudo ground truth. So what we propose in this tracking learning detection paper, which is sort of quite highly cited, you say there are certain events which can be used for regions as pseudo ground truth, and when we learn with pseudo ground truth, we can build a detector for my particular thing. So I think long-term detection of regions is completely possible, but it has a much more difficult start. You might lose something. Okay, you want to track some, okay, some person in a crowd, and if you lose him at the beginning, you lose him forever. But if you try to track something that you recognize as a Suzuki motorcycle that you are familiar with, you will really recover it easily. So there are like, it's not that ocean of a difference, but the prior knowledge will always help much more in objects.
Yeah, definitely. And then maybe a little bit follow up on this for the regions tracking. What's your opinion on the recent surge of the self-supervised tracking literature? Because it seems to be very well suited for this particular problem, right? Where you actually don't give kind of this sort of ground truth thing, as you know, mentioned as well. That's kind of trying to supervise by just, you know, color constancy. I guess you know what I'm talking about.
Yeah, it works like for instance, this principle of forward-backward consistency. So, and I think this type of things appear also in flow, that you can say, well, things which are correct are consistent, and it's very unlikely that something is wrong is inconsistent. So if it's wrong, I treat it as correct, and that can help me do self-supervision, so to speak. So I think this type of methods, like Alyosha Efros' work, has a couple of now well-known papers on this. So I think that we'll be looking for consistency in data that will drive learning and improvement of methods. Like, I think this is a different principle from the principle which was in Angjoo's talk, where the optimization was helping the network. I think see this more in like an expensive method helps a fast one, or sometimes we can also do richer sensing helps the situation for poor sensing. So maybe we can do tracking with RGBD cameras in rooms that will recover D easily. We'll train and you will use this data to run methods which are D. So that's the same thing like reconstruction helps. Maybe stereo will help. So I think we have three things: self-supervision, maybe richer sensors, and there are methods which will generate data for deep methods without actual piles of labeling work.
Yeah, makes sense. Thanks a lot. Does anybody else have to add something to that?
Yeah, I think one thing which is actually interesting in what Yuri said is that to differentiate between the long-term and the short-term tracking, right? That's kind of something I think which people haven't made so much of a difference, and I feel like this is something essential, right? Because it's not the same technology which applies to both, right? And so I think the same thing, how to track regions and objects is also something, even though Thierry is saying it's not, it cannot be unified, but I think it's kind of interesting to think how you can unify these things.
I think even in long term, one more distinction that I think Angjoo kind of mentioned in her talk is shot changes. So I think in a lot of work long term, we still think of occlusions, but we think of it's still one consistent camera, which I think makes a lot of sense for most applications. But then if you want to do anything with mining from internet data, that doesn't really work because there are just so many shot changes.
Yeah, really good point. And it's one of those things that people pretend that it's solved. And so like, you know, doing a shot change detection on YouTube video is like, yeah, you can do it with some thresholding and whatnot, but like it's right now, I think we're at this stage of where, you know, if the shot changes, then you're like, oh, it's a new video, you know, and then lose all of the context of what was happening before. And I'm hoping that that's somewhere like 3D can also be helpful if you were reasoning about the camera viewpoint. Yeah.
Maybe I'll throw in a comment about the sort of short-term versus long-term And this relates to another sort of I guess discussion point of kind of single object tracking versus multi-object tracking. As Yuri points out, that in some ways there's no real reason that like a multi-object tracker couldn't happen to be run on a video with a single object. Like somehow it doesn't feel like, it feels like those terms really refer to how assumptions on prior information about what initialization is given. Are you told, some region in the first frame, or are you not? And then it feels like if you think of a setting where you're not told that information, you're just given some video, then even at sort of at short time scales, you sort of have to solve some initialization problem, which also might reappear at long time scales if if the object leaves the screen and go back. But then the place where I get confused when I start thinking about this landscape of tracking is, so one question is that are the terms single object tracking and multi-object tracking, are those the right terms? And if it's not, then it feels like this notion of initialization it always feels like it's an elephant in the room that we sort of have to acknowledge. And if you acknowledge it, then I think it sort of changes the way maybe we think about short versus long term.
I have one comment here on this topic, single object tracking versus multi-object tracking. So recently we were making a study on recent trends in multi-object tracking on MoChallenge benchmark. We actually recently published a paper on that. And one very, very obvious trend that we noticed was convergence of single object tracking methods and multi-object trackers. So people really started taking methods from single object tracking community and incorporating them into their deep multi-object tracking frameworks. And this family of methods really gave a boost in performance. And actually one of representative methods is actually tractor that Laura talked about. So of course, this method uses very simple single target regressor, not any kind of long-term tracking method, but this was one of clear cases where incorporating such single target regressor really helped a lot.
So, sorry, go ahead.
Another direction. So unfortunately, if the time zone was not the best for the earlier workshop, it was like happening at my 4 or 5 a.m. But so I'm really looking forward to watching the talk too about the single object, multi-object. But another direction is that if there's actually multiple objects, another way that like you could use the long-term context is that if there's multiple objects in the world, then they need to be situated so that physically they make sense. So this kind of using some physical simulation or physical constraints to track them over time for long term would be like another idea that comes to mind when I talk about multi-objects. And that's kind of related to the work that we did with Jason and Deva that will be presented at ECCV, which shows how when there's multiple objects, they actually can give rise to more constraints. And I wonder if this kind of idea is also possible in tracking.
Yeah, definitely. I think now people don't really model interaction between objects in a principled way, right? They're pretty much just written separately. So there's definitely a very interesting direction. Does anybody else have a question?
So I might jump in just because there's some questions on the chat asking, so I might just open up with that. Benjamin asks, what do you guys think about the use of synthetic data for ground truthing tracking applications? So potentially this can get around the problems of long tracklets and get around the problems of no accurate 3D. He mentions perhaps rendering complicated simple crowd scenes, for example. So let's open that up for whoever wants to.
Yeah, so I certainly think this has been a really good approach for single images, and I think certainly we will see this kind of sim to real, like extensive data augmentation could also really help. But really, actually, one thing that maybe I've thought of, like people may not really think about, is that when it comes to motion, actually generating such synthetic data can be quite challenging, because you have to now, you know, animate these people. Like, how are you actually going to animate these people? What kind of 3D data do you have to animate these people? When there's like interesting interaction going on, how you have to write like a planner that goes from everywhere and kind of simulates all of these things. And so in a sense, we would be replacing a 2D joint or, you know, labels by coming up with these simulators in order to generate these scenarios. And I think that's certainly one of the directions that is happening, and I think that's necessary, and it will be developed over the times. But we need to really think about where the source of such 3D motion really comes from. And if we only relied on our preconception ideas of what motion is going to be like, it's not going to be enough. And I think really need to ask the data to what kind of 3D motion and 3D pose prior or 3D interaction is there in real data, and mine that information. And so that would be really an interesting kind of synthetic data. But it's, yeah, I think that's one thing we need to keep in mind.
Yeah, I would say I agree with Angjoo. I mean, the idea of generate synthetic data is interesting, but it's very complex, right? And there are there's this synthetic football play stuff from Google Zurich, for example, around, and we've been debating of using it, but then people say basically the tracking and detection problem is quite simplified on the synthetic data, right? So I'm not sure. I mean, it might be worth a try to see what we can learn from there, if we can learn some new way of initializing the model. But then it's too simple, right? So you need to really generate the real conditions and the hard conditions. And I guess you could say that you generate occlusions, for example, but then they have to be realistic. So it's quite hard. I think it's a good idea, but it's hard to generate this synthetic data. And we have been trying to generate synthetic data for humans. They turned out quite unrealistic, right? I mean, to make it really realistic, it's really hard. So.
Actually, maybe I'll mention this briefly in the talk I'll give, but it seems like, generally speaking, although there's enormous push in using synthetic data for sort of generating training examples, for training for more recognition models, that for like high-level semantic tasks like object detection, that still hasn't quite panned out. But I think what seems to be interesting is that for lower-level tasks like optical flow estimation, it seems like that is a pretty viable pathway. Like state-of-the-art networks for flow estimation, you know, local motion, actually do make use of kind of synthetic data. And so to me, that actually suggests that if you think of tracking as sort of a lower level problem, this question, you know, you sort of delay the semantic labeling problem, that maybe actually sort of training on synthetic data might help if we want to try to do sort of like end-to-end learning of trackers.
Yeah, perhaps we could abstract, right, the actual problem of identifying objects and tracking them. Then it would really generalize much better, right?
Should we take another question from the chat? All right. So one question is, what is the relationship between tracking and video object segmentation? For instance, how different is multi-object tracking versus multi-object tracking segmentation? And similarly, visual VOT versus video object segmentation. I guess a higher level question at the end is, do you think we're moving away from bounding boxes towards segmentation masks?
Surely we are, and VOT has moved. So I think that the bounding boxes are sort of in the past, partially. Yeah, so I think that part has converged already, and it's like there's no reason to output bounding boxes. They're actually difficult to interpret as soon as things start rotating, and it was always a nightmare to say, like, if you like imagine a person exercising and you raise your hands and the bounding box changes completely, and the question is, what is the correct bounding box for objects which are not close to rectangular? You have problems. So the bounding boxes create more problems than solve, and I think that's the bounding boxes are there just like maybe for some surveillance applications to give you an idea where a person is walking, but as soon as you have the bounding box these days, you can have a good guess of the segmentation. So you can even provide to methods which can't do the segmentation. You can give them some specialized segmentation thing that will put that will do like mask RCNN type of thing. If you can get the box, you can get the mask. So I think that's actually the current state of the art. Do the segmentation, don't do the bounding box.
Maybe just for fun, I'll try to give a little bit of a contrarian view, where, so if you talk to, let's say, sort of recent efforts for large scale sort of mask annotation like Elvis, if you talk to folks who've done that, it seems like by far the most expensive part of that were the pixel level annotations. So I could believe that there might be a practical consideration where if you think of trying to collect and annotate data, maybe there's a space for doing some things that are sort of lower cost. Yeah. And then one more thing I did want to talk about with regards to trying to make the connection to video object segmentation. So just to sort of emphasize there that the settings under which they look at it. So for example, if we look at, let's say, Davis, which might be one of the more canonical benchmarks for doing it. So they use the term, I think, unsupervised video object segmentation for when you're not given a mask in the first frame. So when you don't have this initialization, which I think is actually kind of very confusing, because then I've seen other folks talk about, unsupervised video object segmentation is something like tracking by colorization, or you can kind of learn a model just by trying to associate things. But that tracking by colorization would still require some initial mask to then transfer. So that's not actually unsupervised, as according to the unsupervised video object segmentation task. So in my view, somehow one of the things I find kind of difficult in this space, especially as we try to make inroads to other sort of adjacent fields, is the terminology that we use. I feel like sometimes it seems like it could cause confusions.
Yeah, I totally agree. We almost had a paper shot down because we were referring to one of the tasks as unsupervised video object segmentation, and that led to some serious confusion among reviewers.
Does that differ from, to me, this unsupervised video segmentation is motion segmentation of the dominant motion or the motion in the middle or a dominant object. It becomes motion segmentation. Of course, if you say it's an object, you can use a lot of information that what is moving should be an object, and you might have some statistics of background, statistics of objects, appearances, and things like that. But it's essentially motion segmentation. Otherwise, the word video doesn't play any role.
Yes, completely agreed. And we sort of suffer from the difficulty of, well, okay, well, sort of defining what is the dominant foreground motion. And there's even videos there that somehow I wouldn't agree with what has been annotated as a dominant foreground motion, because I don't know, there's a crowd of people observing someone dancing, and there's actually some people moving in the crowd, although the person dancing in front of the crowd is the thing that's labeled. So I can see why. I can see why that's still maybe a difficult answer to actually operationalize in the benchmark.
I would say, give me a single pixel on that object. I think that it's much easier to say unsupervised video segmentation means give me a single pixel on that object, click on it, show it, point to it, than to start arguments about annotating which one is the implicit, automatically chosen one to be segmented. So it's much easier to say one pixel. Because there are many videos where there are multiple things which would be interesting for segmentation. How can it be that every viewer would choose the same object to be foreground? For some things it's obvious, but for many things it's not. As soon as there's interaction of 2-3 people, 2-3 animals, animal and a person, players, ball and a player, you don't know. So let's say unsupervised video segmentation is the video and 1 pixel.
Well, I definitely agree that that's a cleaner way to formulate it, but that's definitely not the way it is formulated in that. But okay, but there are other settings where I assume it can't be interactive, or somehow that initial pixel has to come from somewhere, which if we want some sort of fully automated system for video analysis.
Yeah, I would say basically the segmentation gives you a cleaner formulation, right? Because basically the bounding boxes, you always have this background which you don't really know how to handle, and then if it's different, it kind of strays away. And I guess the reason why people haven't really moved to this segmentation, object segmentation and tracking is that it's actually harder, right? I mean, Jerry might disagree, but I kind of feel, I mean, Pavel and I, we worked on this, and it's actually much harder. You have all this like pixel, each pixel has to be assigned. It's more complicated, and you hit a whole set of other problems. And I think in the long term, we'll definitely move towards this direction, because it's really clean, and you know, when people are overlapping, you know exactly who is belonging, which pixels belonging to what. You don't have this problem about bounding boxes. But I think the thing is that the complexity is somehow higher, and that's why people have shied away. And basically, when we designed Tau, we also thought of annotating segmentation masks, but then it got much more complicated, right? Even just the boxes was complicated enough, but then in addition, annotating the segmentation masks made it much more expensive and much more heavy. And I think something ideally in the best of all worlds, I would just say we have it and give it, but it's really hard to get it, right?
Okay.
Yeah.
Okay, go ahead.
I guess we can move to the next question on the chat, which is, how do we understand the connection between test video frame rate and tracking algorithm? I feel that in a high frame rate video, say 30 or even 100 FPS, a good detector with max overlap match can do most of the job. Is that true? What should be a good frame rate to evaluate tracking algorithm? I think given that Tau is like a data set at 1 FPS, this is a very relevant question.
Well, it's annotated at 1 FPS. The videos are 30 FPS.
Yeah, this is also a question I'm really interested in, because whenever you process these kind of, say, you know, wanted to use the output, it's there's a question of like what frame rate should you be analyzing the motion, and how can you be robust to different speed. But like, yeah, I'm really curious, how do people deal with this in tracking?
Maybe we'll just sort of pipe in. It's another sort of shameless advertisement. So I'll talk a fair bit about in the next talk about essentially a different way of trying to think of benchmarking in what we call like the streaming context. So if you actually have frames coming by, and you have to kind of analyze what's happening in real time, what are the right ways of doing it? And the simple answer, I guess, is that it actually depends. But essentially, rather than thinking about that as the argument that I'm going to try to make anyways, rather than thinking about that as sort of a constraint of the problem, it's a design choice you make that the algorithm makes. So just like we have other design choices we optimize over, we should optimize over essentially sort of like the frame rate at which you process. But in order to do that, there has to be some sort of metric that says, okay, I'm going to optimize this so as to do better on this thing. And so what is that thing? So I'll try to propose some ideas of that.
So in VOT, we touched this by introducing the real-time challenge. And that's where, like, we measure how long it takes to process a frame, and all those that sort of, you miss the frames that you were not ready to collect. So I think the problem has a couple of different aspects. So in principle, maybe it would be best to have a very, very high frame rate video, because you can drop frames if you wish, but you will not ever get the data flow to your process. So you can also somehow deal between treat low resolution in space for high resolution in time. So maybe it should be about data flow. So you would say, okay, we have algorithms, and the amount of data you will be able to process is something like, I don't know, gigapixels per second or something like that. And one could test how algorithms react to lower data rates. Of course, it's still, like, it's not immediately obvious. I guess that if you have, like, for long-term tracking, certain things will not help you with high frame rate, will not help you. If you have occlusions, total occlusions, objects go out of the field of view. It doesn't matter if you have high frame rate, you still have to redetect. So that's one thing. Also, there might be some drifting tendency if you have very high frame rates. So probably you don't have the problems of like jerky jumps where the camera is on a drone or things like that. But I think it's like, probably it would be easier, but the data flow will restrict all applications. So I think it's, but people, okay, there are some, for instance, I think Andrew Davison at Imperial, they have collected data sets at very high frame rate, and you can sort of choose your own frame rate, and you can compare algorithms of different efficiencies and see where you get. So people have touched this. Unfortunately, it's a little bit seems that maybe this will be another dimension on which you benchmark. Yeah, so, which is the unpleasant thing. Something will be very good at very high data flows, and something else will be needed if you have very small flow. Like surveillance situations where you have 1 frame, 2 seconds will work different than 720 frames per second for, I don't know, tracking bees' wings or something like that. Yeah. So, okay, this is a good question, but it's an open problem, and probably there will be some different methods for different situations.
You're muted, Pavel.
Yeah, I mean, I was going to just ask somebody to ask the next question because I already asked questions. Yeah, we have more questions asked in the quick Q&A.
Actually, I would maybe not so much as make a question, but have a comment on how to leverage 3D cues for tracking. So this also relates to the talk of Anya. Recently, as a community, we learned how to learn feature representation from unordered point sets. And as a consequence of that, as a community, we really recently made very quick progress in 3D object detection from LiDAR point clouds. So nowadays we have really reliable LiDAR 3D object detectors that also provide very well localized object detections in 3D space. And there was recently this paper published that pretty much shows that if you have really good 3D object detector, and that in this case we can use very simple data association techniques such as 3D bounding box overlap, so 3D intersection over union, and get really great result. So basically, this method that did that obtained state-of-the-art results on the kitty tracking data set. So I think that this is really one of the recent methods that that showed how important 3D cues for multi-object tracking are. And yeah, maybe there are some more thoughts on this topic.
I think this is like close to related to monodepth and stuff like that. And my only worry is how general is this? Like, I take a video which I download from YouTube, different camera, different conditions. Will the depth be estimated reasonably reliably, or are these things really quite closely tuned to the data set? And so I've recently worked on a problem, completely different one, like separation of reflections, and nice papers. And if you use the methods on data from anything slightly different from their data set, results go terribly down. So I wonder if we see after a while that monodepth works on an arbitrary video very well, then we say, well, okay, if you have an RGB video, we actually have the depth. And if you have a detector, you have the depth because the monodepth will give you that. But I think it has to be seen whether such methods are really as general as, well, I'm not sure that strong claims are being made, but we need to, for this to work in very general settings.
Mm-hmm. Yeah, I would completely agree with that. So here in this case that I was mentioning earlier, there the premise was that we actually had LiDAR measurements with so LiDAR point clouds, which actually provide very accurate distance measurements to objects in the scene. So of course here, if you don't have such sensor input, this becomes much more challenging.
Yeah, and I also agree really that I mean, I think there's a lot of interesting molecular depth approaches, like also in Kitty, but also in other approaches like Midas from Vladlen Koltanslov, which is learning from his 3D movies, which actually works surprisingly well. But I think really it is key that you have to have a method that can also be trained on objects or images or videos in the wild without any supervision, with some kind of cycle that like you start with some bootstrap from 2D approaches, you use some 3D information to make it better, and which can supply more information or label on the current 2D in the wild, and then you can train. And that kind of loop, I think, would be the ideal. But I think where I think the struggle is once you have 3D, you know, you bring it back to 2D, and yeah, completing this cycle seems quite hard, and for other different reasons. Like I tend to focus on very category specific approaches, like humans or animals in specific, and it would be great to do general, but even there, that's a real challenge. So yeah, that's future stuff.
And maybe one thing I'll point out, even with 3D sensors like LiDAR or stereo or any of that stuff, you still have occlusions. In some sense, they're actually like 2.5D. So if a car goes behind a truck, you don't see it in the LiDAR sweep. So so you still have to deal with this always seemed to come up. Partial occlusions are a big pain in the butt. I think that's still true even with 3D sensor data, although it seems like we should be able to sort of do much richer things, and maybe it's easier to identify occlusions. So I actually feel like there's probably an opportunity to try to sort of do smarter things there. And then this question of like, so what can be done with RGB? I feel like it is super interesting to think about all of these sort of monocular depth papers and to see what the current state of the art is. I agree with Angjoo. It feels like things have been improving there quite a bit. Like I had the exact same response that Yuri had, which was for a long time. My suspicion was that they were all very overfit, and it seems like that's changing very recently. That has changed very recently, and it could be then that maybe even if they're not perfect, like I believe that those things still don't give you metric depth, but maybe they give you some qualitative, relative depth that still could be valuable to reason about, potential occlusions.
Actually, since you're mentioning occlusions, one of the takeaways from this recent 3D multi-object tracking papers was for me also that when we are reasoning in 3D space, we can actually devise much more accurate motion models, which of course makes sense. And then in turn, this really helps with occlusion.
Yeah. And another point I wanted to post is that like a lot of videos don't have moving cameras, right? So a lot of like, if there's no motion, it's difficult to maybe gain some kind of cues. And there's certainly lots of videos where there might not be that much camera motion, but the objects are moving around. And another thing I would add is really like onto what Deva just mentioned is even in LiDAR that might be 2.5 and you want to deal with occlusion, and in order to do that, like what you just mentioned, I think temporal cue and like motion prior is another really interesting direction to kind of fill in the gap. If these are, it's kind of like temporal imprinting, and you could use that to track it. At the same time, in order to do this, then you need a really long video to apply any kind of like sequence-to-sequence kind of approaches to be more robust to this. And currently the data gets kind of chopped at every single shots or disocclusion, which makes it actually impossible to get there. So I think it's a little bit of a chicken and the egg coming, at least in a case where there's no camera motion.
How much time do we have left?
I think we're 10 minutes over. So maybe, we can ask like maybe one more question, or we can ask you can ask your closing question, and then we can close it off.
Okay, yeah, I guess, yeah, then I can ask my closing question, which is going to be basically, because this dataset, this workshop, we are kind of pushing the idea of generic tracking, right? Trackers which can work in any environment, in any situation. But at the same time, we kind of already know that tracking can be made to work in specific scenarios by just engineering, right? There's a lot of applications where people actually are making tracking work pretty well in a very limited environment. So the question is what we're doing even worth it? Because I know a lot of people don't think so. So a lot of people think, like we even got this comment in the reviews, right, that said that basically tracking is an engineering problem and it shouldn't be solved in general sense, it should be solved like in every particular application. So I want maybe to hear something encouraging from you or discouraging, like, do you have any reasons why this is a good problem to work on? Like, do you think it's actually important to solve a generic tracking problem?
Well, I think I would say that you don't want to hack up your tracker for every specific application, right? Basically, obviously, if you know that you're dealing with a self-driving car or something, you can tune your tracker to the application. But then if you want to have it work, for example, with generic movies, I think that would be for me a typical example where you want to have it work all the time. And that's something where today we're very far from getting it to work, right? And so basically, I think we're still missing some technology components or some methods which really make it general. And then you could still say you want to fine tune the approach on your data, right? I think nothing wrong with this, but you don't want to design a new method every time you change your camera, right? And that's kind of, I think, what the reviewers don't get. They don't get also that basically there's a lot of variability even in the same kind of, so for example, if you look at movies, I mean, there's so much variability that even there you would need to start hand tuning stuff. And I think current approaches to tracking, they have gone down this road of hand tuning a lot, right? So they have this benchmark and then they tune on this benchmark. And then if you change to another benchmark, your approach doesn't work anymore. That's clearly something which is not satisfactory.
Yeah, I think I'd like to add on to that. I totally agree. I think it's unfortunate that that kind of comments happen. I think in a sense, like it's maybe similar in the sense that under a supervised, I think we've become really good at solving supervised problems. So under like supervised setup, we may know how to do these things, but I think it's completely wrong that tracking is somewhat solved or just engineering, because when you have a new task, maybe if you wanted to interact in an active setting with other humans or something like this, certainly the algorithm, like the final task may not be tracking in particular, but in order to solve many interaction tasks, you need to be tracking objects in order to make high-level high-level decisions or directions. And for those, you need some kind of backprobable component that can like do these kind of association on its own. And I want to do it, but it also is a lot of it might be actually currently engineering. Maybe I'm wrong, but like that's certainly the impression that I get. And like it would be, I know there's some works that try to make it end to end in a sense with the graph convolution neural networks, but perhaps maybe I'm just not aware of those. But another thing is like a lot of the tracking setup is very specific to the data set. I think I would like to see more future work that shows like general setup of tracking. It's really hard. Once you have put a data set forward, the field, the community solves it. And there's a lot of like empty areas in that real data that we haven't really looked at. For example, like super crowded, Tokyo street versus like two people dancing, maybe like not that complicated, but still have lots of challenges that are to be explored. And so that kind of, look, it's actually not solved might be like a good paper to write. Or I would love to see that.
Yeah, I would like to add to this answer that it has two parts. One is education of the reviewer and like how to deal with reviews, because and the second thing is in the long term, the general method will be better than the specific. So these days, nobody writes his own least square solver because the general one, which doesn't exploit maybe some specific constraint in their application, there's so many years of development in there that method works in almost all conditions extremely reliably. And we have to work towards that end, that your particular solution for your particular application will have many more bugs than applying the general stuff. And the fact that we don't have it means that at the moment we have to have a compromise, okay? We do something specific, but that's dangerous, buggy, non-robust. In the long term, I think you can always see it in detection. Like it's so much easier now. I don't know, in medical imaging, they want to separate two types of cell. They take a standard net that we use, and in a couple of days with the data set, they have the solution that they haven't been able to do in dozens of years of particular algorithm development. I don't know, this retinal Kegel challenge comes to my mind. So I think the methods which will be general will in the end will be robust, strong, and the best. I believe that.
I also have another argument that comes from the area of developmental psychology. So basically, there's quite some evidence, from what I understand, that babies already learn to segment and track objects via self-supervision. So basically, supervisory signal comes from interaction in the environment. And this happens already at quite early stages. So they can track and segment objects before they know what objects really are. And this also relates to what Yeri was talking at the beginning, that tracking is something that probably happens before recognition. I think that if this is how us humans learn, this is also quite a strong argument why tracking actually should be generic.
Yeah, I mean, I definitely agree with all of that. So thanks a lot for you. I know, Deva, do you want to add something else?
No. It's great to hear. Yeah, just building off, it's something that I've always sort of thought of myself is that, yeah, given all the successes that we've seen in detection and other sort of vision problems, it still amazes me sometimes that that like the tracking isn't solved yet. And maybe it's not fair to say that detection's solved yet, but like the kind of innovations we've seen in those other settings. I guess I shouldn't be asking a question, but I oftentimes wonder, so what's holding tracking back from seeing the same inroads? I don't know, maybe it's data, maybe it's compute. I guess there's lots of things that have been sort of suggested.
Yeah, it's funny that people think this way, right? It's like, as a vision researcher, you should know that this is a really hard problem. But I feel like in order to make progress, we were able to compartmentalize the kind of situations. And certainly in those places, there are like real, developments. But if you just wanted to take a YouTube data, there's so much pre-processing you still need to do. And it would be really great if it was a lot more general. And people need to really think outside the box of data sets and really think about real challenges in the thing. And I think I agree with this reviewer education or junior students. Like, it's really not like just there's new things outside your world of current data sets, and I hope we can encourage that kind of work.
I think the progress actually in tracking by segmentation and video object segmentation is very significant. And I think what is holding back this 3D tracking, we saw how difficult it is to solve a very specific problem, the human body, articulated body, lots of measurements, lots of data, and still it's very difficult to model that. And now we are talking about modeling anything in 3D with all the degrees of freedom. In detection, we sort of say these are sort of variables that I don't want to know. So I think what we can do, we can label the thing, we can segment the pixels which it covers, and now we have lots of degrees of freedom for articulated objects and non-rigid objects and so on, where we have problems with modeling that, representing that, and maybe with spatial reasoning and all these things. So we are sort of opening problems which have been hidden. Actually, the detection problem is a breakthrough. People exploit it. It seems that, but maybe when it comes to robotics, where you need to deal with physics, 3D world, affordances, manipulation, maybe the fact that we progress in a huge area makes us over-optimistic, but there are a lot of other problems, and tracking is touching this problem with 3D representation of the world, objects, non-rigidity, and so on.
yeah, I guess at this point we just want to thank again all the speakers. Thank again for your comments, for participation, and we'll have to wrap up and move to the next talks, if everybody agrees.
Thank you.
Thanks,
Thank you.
everyone.
Okay, thanks. A nice session.
Thank you.
Okay, so resuming our speaker sessions, I am honored to invite our next speaker, Deva Ramanan, who is an associate professor at Carnegie Mellon University and is the director of the CMU Argo AI Center for Autonomous Vehicle Research. His research interests span computer vision and machine learning with a focus on visual recognition. For his fundamental contributions to computer vision in the last many years, Deva has been a recipient of over 8 awards, including the NSF Career Award, Pascal VOC Lifetime Achievement Prize, and the IEEE PAMI Young Researcher Award. Being associated with Argo AI as a principal scientist, Deva has long worked in autonomous vehicle research, which is one of the most prominent downstream applications of object tracking today. I'll hand over to Deva to hear his take on the role of tracking in autonomous driving.
Okay, thank you very much. Okay, so I thought I could give, as Trasha mentioned, I've spent the last 3 years on sort of partial sabbatical at a self-driving company, sort of digging in a very sort of, I guess, intense way to vision and perception in a real self-driving autonomous robot. And it's been, for me anyways, it's been sort of fun and kind of eye-opening to see the kinds of challenges that are addressed there. And to some degree, that's been one of the huge motivations for focusing a lot on tracking. And I'll try to give some sort of samples of kind of lessons that we've learned along the way, and then open problems that I think still remain. Okay, so the context that I'll give this talk is very much from tracking for robotics, or tracking for. I like thinking of this in terms of embodied cognition. There's a body moving around, perceiving what's happening in the world, and trying to act in it. Okay. So first, I want to kind of motivate this by thinking of sort of recent challenges and sort of somewhat, definitely catastrophic failures. So Bastian, in his talk, also kind of motivated his talk by looking at recent failures of self-driving cars. And so this is one where I actually think it's sort of interesting to dig into. So there's a lot of federal oversight here. So when one of these bad things happen, you can go download a safety board report, NTSB, which actually goes in pretty exhaustive detail about what went wrong. And it talks about many levels of what went wrong, but in particular, it also talks about vision and what was difficult about the perception stack. And so this is a sort of copy paste from this federal report. So what I'm showing here on the table is a list of perceptual inferences of the vision system. So this was a case where there was a person on a bicycle who essentially popped out of an occlusion sort of in front of the autonomous vehicle, and it didn't stop in time, and it was unfortunately a fatality. And so this is sort of a frame by frame or millisecond by millisecond report of what the vehicle thought. So at some point it thought that this person who was walking a bicycle, who sort of popped out of an occlusion, was itself a vehicle. Sometimes it was actually labeled as an other category. It's not clear what this means. There was no semantic label. Sometimes it was labeled as a bicycle. Sometimes it was labeled as other as well. And if you read the summary of the report, it says the automatic driving system changed the pedestrian's classification several times, alternating between vehicle. Oh, boo. All right, so this is cut off a little bit, I see. Okay. Well, I think it's just that slide. Okay, alternating between vehicle, bicycle, and other. Because the system never classified the pedestrian as such, and the system's design excluded tracking history for non-persisting objects, those with changed classifications, it was unable to predict or forecast the pedestrian's future path, and that's what caused the collision. So what this says to me is that in some ways, it's the point I want to make is that it's fundamentally challenging to come up with robust interpretations of a dynamic world. In some sense, they're almost like oxymoronic statements, because if the world was static, then we could kind of build up some robust interpretation of it over time. But if the world is changing, if at any point something can pop out of somewhere, and I have to react to it, then I almost have to allow for my perceptual understanding to be very dynamic. And so another sort of manifestation of this is a lot of times when we look at tracking outputs, or if we look at single frame outputs applied to frames of video and we see flicker, usually that's one of the arguments that we hear for, oh, that's why we need temporal processing, because by doing that, we can remove the flicker. But the other argument I want to make is, if you think about this in a truly online fashion, in a weird way, maybe the flicker is good, because the flicker is reflecting the capability of the system to correct itself. It mistakenly thought something else was happening before, but now it sort of switched gears and now it believes this is happening. So flicker almost reflects the ability of the system to be very reactive. Another way to think about that is, one way to sort of smooth out and get sort of temporal consistency is you literally average things over time. But by averaging, let's say you could average the semantic label over 50 frames, that means that you're going to have a 50 frame delay before you react to a change in the environment, which is also a bad thing. Okay, so so this has kind of motivated this argument for, and I think that if you sort of embrace this view that what I'm showing on the left-hand side is a result of a state-of-the-art object detector applied to frames from a video, and on the whole, it looks surprisingly good. And once again, this is a per frame method. There's no temporal continuity applied here. And it could be that if you embrace this notion of I want to build very high accuracy representations that are very reactive to changes in the world, then maybe actual single frame processing is a good way to go. And personally, I think this is why there's been so much effort on single frame sort of innovations. Like a lot of the great wins in detection and image analysis and classification really focuses on single frames. And so you can imagine, but if we want to do this in real time, what we really want to be able to do is process a frame before a new frame arrives. And so this statement that I'm making is, I think is very well acknowledged. And so this is why a lot of, let's say, contemporary papers on object detection tend to have graphs like we see on the right-hand side, where we show, accuracy, MAP on one side, and then millisecond, the amount of time it takes to process on the other side. And usually there's a trade-off. And one of the, I think, biggest knobs we can use to explore this trade-off is, we swap out a deeper backbone and then we'll get higher accuracy, but it'll take longer. Or we can play with resolution. It also has like a profound effect on, processing a 300 image is much quicker than processing a 4K image. Okay. So, but what I want to claim is that this is not the whole story. And what I mean by that is, so this is the visualizations that we're used to seeing in vision. And what I claim is these are all offline visualizations. If you actually sit in the brains of a robot, if you sit in a car while it's moving, what you see is something very different. And what you see is something that looks like on the right-hand side. And this took me, this is a bit embarrassing, but like 2 years to really figure out what was going on. Because everyone always told me this was a visualization bug. That, oh, what's happening is that we're just not seeing the frame that was processed. And now there's some sort of indexing error. But my claim is what we're actually seeing is the true real-time analysis of what the system thinks it's happening. And it comes from the fact that any finite time algorithm, when you give it a frame and you process it, by the time it finishes, the world has changed. And so almost by definition, the output of what the algorithm spits out is stale. And this is at some level undeniable. And so this notion that we always have to work with these sort of finite time, like time is a resource that we can never get back, is actually a very old idea. So this goes back to Herb Simon. So he had this terminology for bounded rationality. This phrase that, okay, essentially if we're going to try to build intelligent agents, back in the early days of AI, people tend to think of trying to build intelligence through essentially treating it as a search problem, where you write down some optimization problem, you try to figure out the optimal path through some graph. And his argument was that, well, no, that's not the right way to do it, because we'll never have the resources to actually optimize that. And so we have to kind of model everything, model true intelligence with the fact that we're resource constrained, that we only have limited time and limited sort of compute. And incidentally, this also sort of had enormous ramifications for behavioral economics. So this is one reason why humans don't behave rationally, why they don't make the optimal choices all the time. Because a lot of the time, they don't have the resources or the time to figure out what the optimal choice is. You kind of have to make a choice and go on with it, because in 30 milliseconds, you might be colliding with something. So you have to make a decision about what to do now if you're a self-driving car. Okay. So one way to think about this, if we take a step back, is really embracing this thought that we've heard a bunch of times, which is, let's think about how tracking and visual processing affects the downstream application. So we can think about this ultimately as if I'm a robot, I'm perceiving so I can act in the world. So we can think of this whole level system and this whole level system of I should really measure the accuracy with which how well I can act in the world. So if I'm a self-driving robot, maybe my final end-to-end metric is the number of takeovers I have. And what I should really do is I should tune my perception system and my tracking system to minimize the number of takeovers. So the argument was that if we look at this graph and we think of different kinds of, let's say, points on this curve, it could be the case that actually using a worse method, but that's faster, might actually result in better overall behavior because I can be more reactive to the environment. And so this to me was really surprising because I always knew that, or it always seemed natural to me that, okay, if I use a worse method, if I'm willing to make do with sort of lower accuracy, I can probably shave off some latency. I can have a faster runtime. But this is saying that actually, if I move even along this Pareto optimal trade-off, there might still be a sweet spot that allows me to behave and act in as safe a manner as possible. So that suggests that if we could actually do end-to-end optimization, maybe that would already figure out this sort of compute trade-off. But of course, that's actually hard to do historically because number one, you don't really want to drive around and see how many times you run into things because that's dangerous. So instead, it seems like as a community, it's actually been incredibly useful to define essentially proxy metrics that in some sense, we don't go all the way down to the downstream task. We abstract away and we define things like MAP, pixel classification rate, or even MOT or HOTA or any of these variants where by abstracting away the end task, we can still kind of innovate and kind of come up with sort of better perception algorithms on our own. So the hypothesis that we want to make is that there's a slight modification that we can make to our own metrics that we use now that actually takes into account this notion of being able to perceive in a real-time way. Okay, and so now I want to ask ourselves, what is the right definition of real-time? And so something that we've heard before and that I think is implemented fairly commonly is real-time means that you finish before the next frame arrives. But at some level, I want to argue that this must not be the right way to think about it because that's dependent on the sensor rate. At the very least, different sensors operate at different rates. So if you were to apply this definition to LiDAR, LiDAR typically operates at 10 hertz. So you get 100 milliseconds. And then somehow it doesn't seem philosophically correct to assume that, if a child appears in front of your street in between two temporal samples, that you're not responsible for perceiving or acting until you see the next sensor measurement. Like at some level, the argument I want to make is that we act in a continuous time world, and so we should perceive in a continuous time world. So then the claim I want to make is what we're going to do is essentially come up with a way to think about metrics where we require an algorithm to report the state of the world at all time instants, even if it's not done processing the previous frame. And if by default the algorithm doesn't report anything, we'll just sort of use the last report that it did give. Okay, and what this essentially means is you can think about this notion of anytime you have a single image or single frame metric, you can essentially use this philosophy to turn it into a streaming metric. So if we had things like AP or pixel classification rates before, we can now turn this into a streaming AP or streaming pixel classification rates. And the way that we do this is essentially, you just essentially run your algorithm in your actual hardware and you look at the output. That's what we're seeing on the left-hand side. And you just compare those predictions to the actual ground truth on the right-hand side. And what you find when you do this is that, essentially almost all methods dramatically decrease in accuracy. And so as one way to kind of relate this to sort of previous work, this is very evocative of things like anytime inference. But usually that kind of work oftentimes had this notion of computing on a contract. where an algorithm must finish processing before the next frame arrives. But in this view, what we're trying to advocate is no, the algorithm can decide what frames to ignore versus what frames to process. Okay, so so in some sense, here's sort of a preview of the results. So if you just take an off-the-shelf detector and run it, it'll look something on the left-hand side, and it gets very poor performance. The first maybe high order point is that when you measure accuracy on your single frame tasks, you do way worse than the offline accuracy that we measure. And by essentially defining this metric, this streaming AP, and trying to optimize your learned network for this metric, you can recover about half the performance drop. And so you get a bunch of the performance back, but we're still not fully there. And perhaps what's even more interesting is that when you try to optimize this single frame streaming metric, a bunch of sort of interesting behaviors emerge. So I should say this will be a talk in ECCV this coming week by Martin Lee. So I encourage you folks to attend to hear more information. But here's a couple of solutions, sort of interesting things that happen when now you optimize streaming AP as opposed to AP. First, what you find out is that along this Pareto optimal curve that trades off performance versus latency, there's actually a unique sweet spot that maximizes streaming AP accuracy. And the thought is there's sort of two extremes. You can imagine running a really fast detector that finishes before the next frame arrives. But then that becomes so inaccurate that has horrible performance, like 6% AP. You can alternatively go to the other extreme, run a super accurate detector, but then it takes almost 700, almost a whole second to process. And when you do that, you get great, high accuracy outputs for a frame that's, very stale, 700 frames ago. And so because it's so stale, you get lower performance numbers. And it turns out that you get a huge bump just by picking a point in the middle. That roughly takes about half the time between either of them. The other sort of interesting thing that emerges when you optimize the single frame metric is that tracking and forecasting emerges internal representations that help you solve the streaming image understanding problem. Essentially, you could think of instead of just naively copying the last state of the world that the algorithm opened its eyes and actually processed a frame, you can think of that as almost like a 0th order hold. And what turns out to be much more effective is you do a 1st order hold. If the last time you saw the world, you could also estimate some notion of local velocities. Then even if it's something as naive as 2D, then you can just sort of pretend that the world evolves linearly when you're not watching it. So you just push things forward by the estimated velocity, and this gives you much higher accuracy. But importantly, all of this is done in a kind of compute-bound context. And so here, tracking and forecasting only makes sense if they're extremely lightweight. If it ever would have been essentially cheaper to run another detector, you don't really see a benefit of doing it this way. So this forces us to come up with like very lightweight solutions. And then finally, one of the really sort of surprising results that happens is there's this tendency when we run these systems in a robotic setting that everything is very asynchronous. So you're processing some sensor frame and there's a little bit of stochasticity to when you finish. And then usually when you finish, you just grab whatever remaining sensor is available in your sensor buffer and you start processing that. And that's how I've seen sort of most of these robotic systems run. But what's kind of surprising is when you formalize this streaming AP metric, you realize that sometimes it's actually better to wait for a new frame to arrive rather than begin processing the old frame that you have lying around. So we would call that the idle free method. So this waiting is visualized by this yellow block. And the intuition is that if you finish just before a new frame arrives, sometimes it's better to sit and wait for that new frame. So now you'll start processing fresh data rather than processing an existing frame that's going to quickly become stale. So what was kind of very unintuitive about this is that sometimes, when you're trying to build a very reactive streaming system that is able to react to changes in the state of the world, sometimes the optimal thing that you can do is wait, which is very counterintuitive. And ultimately, the sort of optimal solution that we found is essentially you have to learn how to schedule yourself a little bit. You have to learn when you should wait or when you should process the frame in hand.
Deva?
Yes.
Quick, so there's a couple of questions. I don't know if you want to take them at the end or if we should stop you in between.
Got it. Sure, sure. Why don't I just, there's a natural place for me to pause, and then I'll ask a question. Okay. And so even though I sort of motivated this from the perspective of, building like an actual system to run on a physical autonomy stack, but one of the inspirations for us was always actually sort of biological vision and biological perception. So the human reaction time is roughly 200 milliseconds. So what that means is the time it takes from, like a sort of a signal in your retina that fires to go all the way to your fingers to manipulate a bat takes roughly 200 milliseconds. And so if you're actually hitting a ball that's moving at 100 miles an hour, what that means is the visual signal you're using to actually ensure that you're going to contact it is actually, you're using an image of a ball that's 30 meters out. It's actually very different than where the ball is when you're hitting it. So that suggests that you must be doing some kind of forecast in order to actually react to your environment. And so there's plenty of evidence from the sort of human vision literature that suggests that people make use of these kinds of sort of asynchronous processing. Okay, so let's see. So that was sort of the high level vision, that if you think about trying to build, maybe if nothing else that you guys walk away with from the talk, if you think about trying to build sort of truly online streaming systems that can understand the state of the world and react to changes in it, then what's kind of neat is if we just use our traditional kind of single image metrics, but embedded in the streaming fashion, then what emerges is that you really need high precision tracking, and you also need to forecast what's happening a little bit into the future. And so what I'll talk about in whatever time is remaining is that there's a bunch of, I think it's sort of an interesting time. So I imagine a lot of people working in tracking don't really think about forecasting. But there's a bunch of cases under which I think it's an interesting time for the communities to merge. And so in the time that we have, I'll sort of talk more about that, but I'm happy to take questions now. I don't know if I can see them.
I think if you open Q&A, you should be able to see them, but I can also just ask them to you.
Q&A, so you guys can see my screen, correct?
Yep.
I'm pressing Q&A, but I don't see it. Ah, here we go. Okay.
I guess the first one for the roundtable, so I dismissed them.
I'm sorry. Oh, maybe it was already naturally answered. Okay, this is what I'm seeing. Okay. How do you think it relates to humans to tracking? Got it. Okay, hopefully just answered that. When the algorithm should process a frame, the motion of the car, process frame during complex maneuvers more often than compared. Yes, so there's a bunch of factors that applies. So you can imagine this notion of like, when should the right time to sample a frame? It depends on the complexity of the scene. And a huge part of that is sort of influenced by how much you're moving, because that changes sort of the scene you see in front of you. And also it depends on the sort of trade-offs in the algorithms, in the Pareto-optimal algorithm space that you have. Like maybe you still can get a pretty good estimate of what's happening pretty quickly if you trade off a little bit of accuracy. So yeah, there's a bunch of interesting sort of questions about when this would apply or not. Okay. So in the interest of time, maybe I'll sort of quickly go over a couple of other things. So I want to sort of divide into some of the work we've been doing with tracking, and then also give you a flavor of some of the things in forecasting. So first, with regards to tracking, something that was sort of hinted at before, but what about the use of synthetic data? So I just wanted to point out the work that former student Rohit Girdhar did on essentially taking one of these existing synthetic data sets and turning it into a tracking data set. Sort of mentioned before that it seems like this kind of data, even if toyish, seems to have been useful in constructing state-of-the-art flow algorithms. Not exactly this data, but things like flying things 3D that will have a little bit of this flavor. And so this question of, can we use this kind of data to solve tracking problems? And one of the sort of particularly interesting places, so you can do things where things are covered or occluded by other things, or even contained by other things. And those are cases where it's typically hard to get lots of labeled data. So maybe it's a place where synthetic data would be fun to see. Maybe we'll just sort of skip here to, one particular place that I just wanted to highlight is, if we really embrace this kind of online streaming view of the world, we've already talked sort of quite a bit about how occlusions are one of these big challenges. And what you generally hear from the tracking community, so here's a case of someone being occluded by a car, and at some point they're almost fully occluded, less than, let's say, 5% of the pixels are visible. And I think traditionally in the tracking community, maybe a reaction we might see here, oh, this is where re-ID should kick in. Because when the person reappears, I want to be able to link their appearance to what they've, the last time that I did see them. But in the online streaming context, I don't think that's enough. Because while they're occluded, I still want to reason about that, that there's a potential occluded person there. This goes back to, someone hearkened to this notion of, object permanence in young infants. It's incredibly important from a behavioral standpoint that maybe I slow down because I think a person could possibly be there. And so this, I think, very much comes up in the online setting, because in the offline setting, it does seem like you can make do with kind of like finding an object when it reappears and stitching it together. So essentially, one of the arguments I want to make is that even though we've formalized tracking, there's online benchmarks and also I guess sort of offline video processing. My hunch is, as a community, we still haven't really embraced streaming computation yet. And another example of this is even if you go into how code bases work now for object detection or single frame analysis, they're almost all optimized for throughput, because we always think of we're going to operate on batches of frames, and that's not the right way to think about optimization in the streaming context. There, the crucial quantity is latency. And so sometimes there's even pre-processing steps of like image resizing that sometimes current code bases do in the CPU while batch data is being prefetched, but that it totally adds a huge amount of latency if you're trying to do things in an online fashion. So my hunch is there's even design and compute choices we've made that we probably don't even realize are really geared for batch processing on the cloud with mini batch sort of frame analysis, which I don't think is the right way to think of online streaming computation. Okay, so I won't sort of talk about TAO. We've already talked a fair bit about this, but and I'll wholly agree with one of the comments that that was sort of brought up, I think quite a bit by Yuri, of it's really important that we need to be able to track objects without even naming them. The example I always give is a piece of trash, a trash can that falls over and we see little objects running around, sort of rolling around. I don't think I'll have detectors for every piece of trash in that trash can, and I also don't think I need them. But I'm still able to sort of track and segment and understand how things are moving, which seems super important. And in fact, I think one of the cool things about TAO is that this notion of one way to sort of figure out what objects should be labeled is we actually look at what objects move. And although that might sound like a trivial observation, that actually is inconsistent with a lot of high-profile benchmarks out there. So if you look at cityscapes, interestingly enough, they do not label strollers or people in wheelchairs, just because that, I guess, it wasn't a common enough occurrence. So this sort of pixel, these are the white pixels that are labeled in this image. So when we kind of sit down and try to write down ontologies about the vocabularies of things that we're recognizing, we oftentimes like implicitly cut corners so as to, I don't know, make the task easier to address. But clearly from a behavioral analysis point, it's incredibly important to realize that that's a stroller there, that probably there's a child in there. And so using motion as a cue of, okay, well, let's first start by labeling everything that's moving, I actually think is kind of an interesting way of constructing ontologies, which is what TAO actually does. Let me skip that for the moment. Another thing that I've been super interested in terms of trying to build really good open world trackers is to say, well, how do we actually solve this initialization problem? How can we build a generic object detector? And so this feels like, we could sort of, what does it mean to build a generic object model or a generic object detector? And this seems to harken back to things like perceptual grouping. So how do we define what an object is? Well, it's a bunch of pixels that look like each other, that are symmetrical. And what I suspect is a super important aspect of that, there's also a bunch of pixels that move similarly or a common fate. And so there's a bunch of, the thing that always kind of, it's hard for me to, I always come back to is that if we think of trying to solve the self-driving problem of understanding and tracking the world so I can navigate it, flies evidently solve this problem, rats evidently solve this problem, and they probably aren't doing it anywhere near the way that we've built our systems. And it seems like there's biological evidence that suggests that motion plays a huge role. So we've been doing a bunch of work of trying to extract motion-based cues for building generic object detectors. So here's this kind of cool, cute visualization of, okay, so when you think of motion-based cues for detecting, recognizing objects, optical flow is probably the workhorse sort of tool there. So at every pixel, we spit out a UV vector that tells you where it's going. It turns out that if you kind of think a little bit from this biological perspective, what you can also extract for every pixel is whether that pixel is getting bigger or smaller. So this is sometimes called optical expansion, and there's a way to infer this using the divergence of the optical flow field. But what's cool about that is basically when things move closer to you, they get bigger. It's sort of an obvious statement from perspective projection. What they will tell you is that if you measure local pixel expansion, that can give you a clue as to whether something is moving closer or further away. So what I'm visualizing in the bottom sort of black and white image, although it looks like a 3D depth map, it's not. In fact, if you just look at it, you'll see that it's ignoring a bunch of 3D structure. What that literally is, it's an expansion map, and you can show if you derive this a little bit, it essentially tells you time to contact, which is actually sort of a classic biological clue. So it turns out that you can use this as almost like an in-between representation between 2D flow and 3D scene flow. But this thing actually is kind of reliable to extract from images. So we have some work on sort of using this to actually help upgrade sort of an analysis of a dynamic 3D scene, which ultimately you could argue is what we really want is something like 3D scene flow. And I'll sort of skip about how we do that. It's actually pretty simple. It's based on this intuition that if things look bigger, things are getting bigger, then they're getting closer to you. And now that we have this kind of 3D-ish scene flow, one of the things we can do is actually look for moving things, even when the camera's moving. And so essentially, Yuri hinted at this a little bit, like if we could actually extract, essentially what we're almost trying to solve here is a problem like multi-body SFM or multi-body SLAM. We're trying to estimate the rigid scene, and then we're also trying to estimate rigid objects that are moving differently than the rigid scene, which is really the camera motion. Something that this might have been a well-known result. Well, we found a reference for this, but something I didn't realize is that if you look at this image in the top left, where this car is actually driving the opposite direction, and if you're given sort of the perfect 2D flow from this, you can ask yourselves, can I actually infer that there's a moving object, that car in that opposing lane is actually moving? And it turns out that's actually not quite true. You can't. There's a 3D interpretation of the scene that's consistent with the 2D flow, which is it could be there's a really big car that's floating above ground. Of course, the reason why we don't believe that is I think we have a lot of other contextual constraints. But what sort of is kind of interesting here is that by digging into this kind of 3D-ish flow that you can extract, we can try to build systems that will segment out multiple rigid bodies. And here's a visual of this here, but it's a little bit hard to visualize because there's sort of two moving cars in this setting, the white van in front of us and the car to the left, and everything else is static. The other point is intentionally wanted to do this from as little temporal data as possible in order to make the system reactive. So 2 frames is almost the minimum you can use to estimate this. And another sort of interesting point that for folks outside this area, it turns out that it's incredibly and surprisingly hard to tell the difference between a stationary car and a moving car. And the reason why is you can imagine someone is just about to move out of their parking spot. So at that instant, they're actually moving very slowly. And so it's really hard to distinguish between very small movement and no movement. But what's kind of surprising, if you think about it from the behavioral response point of view, there's a huge difference about how I should act if I think someone is pulling out or if someone's actually parked. So this notion of being able to really estimate if something is moving or not is I think actually profoundly difficult, much more difficult than you might have thought. So the hope is we sort of use tools like this to initialize trackers, or maybe sort of use this in concert over multiple frames to sort of build systems that can understand how things are moving and evolve. Okay, and so you can do things like now essentially detect and segment out objects you've never seen before. Like in this case, it's a person riding an e-scooter. Right now, you can't download an e-scooter detector. But using this kind of system, you can get these inferences. Just in the interest of time. I assume I'm way over.
Yeah, but you also started way over. I think if you account for when you started, I think you're a few minutes over.
Okay, so I'll just quickly summarize. Okay, I'll sort of just, I won't talk about the forecasting bit because maybe it's a little too astray here, but I'll give two more, one quick high level point, because someone brought this up. You know, one of the discussion points in the panel was really integrating tracking in 3D. One of the points was actually, you know, in terms of 3D processing of, I guess, of LiDAR points, there's a lot of innovation. There's been a lot of cool, you know, deep detector work. Just for folks that may not have seen this before, on the left-hand side, it's a top-down aerial view of a LiDAR sweep. So that black circle in the middle is an autonomous vehicle, and this represents structures all around it. You can actually see lots of parked cars that are oriented at 90 degrees. And so what this is sort of pointing out is that if you looked at two particular regions, those are drawn in the red ovals, and you tried to run some deep detector, you might kind of locally extract points and encode some feature descriptor. And in both cases, maybe the local descriptor looks really similar. But if you actually think about the free space, which is the fact that whenever you measure a LiDAR value, an XYZ point, you're also told that there's an empty ray in between the LiDAR sensor and that point. This actually paints a very different view of the scene. So you now know it's very unlikely that there's something in free space, but maybe there is something that's occluded beyond your line of sight. So it turns out existing representations for, you know, point nets don't encode this because they were really made for what I would call sort of 3D mesh data where you can see hidden surfaces. But the kinds of data that we actually see in from these sort of censored 3D measurements is actually 2.5D. It still has occlusions. So it turns out you can kind of try to kind of augment those representations with these sorts of occlusion models. It can actually do, it can actually help quite a bit if you're trying to find things like partially occluded cars, because you can much better reason about, oh, it's okay that I don't see the rest of the car here because I shouldn't, there's an occluder. That's actually kind of an easy thing to extract just by raycasting. And one kind of exotic thing that we're just sort of toying around with, and this is kind of a controversial claim, which is it could be that when you think of navigation, maybe the crucial point is really, maybe I kind of believe this, it's really about understanding free space. It's about understanding what's empty that I can move into. And if that's the case, just by raycasting, and in particular by raycasting in future frames, I can figure out what the future free space will be. So it's possible that I can actually use that as a training signal. And what's kind of striking about that is that no annotation is needed. So we've hinted at, you know, supervision is a crucial issue here. And now, you know, if you think of the sort of millions or billions of miles of this kind of data that's being collected, there's, I would say, less than 0.1% of it is annotated with boxes. And so, you know, 99.9% is just the raw data, but maybe we can actually use that as a training signal for understanding where free space is in the future. And so it's this kind of certainly controversial claim that, you know, we're sort of using tracking as a fundamental sort of representation that hopefully will enable things like moving around and reacting in the world. But maybe there's settings where we don't necessarily need it, or it'd be cool if we can use this sort of thing at least to maybe augment the sort of tracking data that I do have labeled. Yes, and so maybe I'll end there. The kind of take-home messages then. So this first point about like it's essentially embracing temporal processing and streaming processing. One reason where I think that maybe that could even apply. So one point of fact is that I believe that kind of analysis is actually needed in a true embodied setting, where if you're trying to perceive and react in real time, in true sort of instantaneous, continuous real time. One place where maybe that also has an effect, even for offline processing, is, you know, one of the things that was sort of suggested before is that processing videos is incredibly time consuming, and that's one of the reasons why innovation has been hard. But maybe by adopting a very, you know, streaming online lightweight model, we can actually turn the compute constraint into a win, where we can sort of design much more lightweight solutions. So maybe that view actually applies to, you know, video processing in general, just to make things more lightweight. So in the world of tracking, what that view suggests is that it's super important to track and also super important to forecast. And one of the things that I think is will be incredibly important in the future is how do we actually track the sort of large universal vocabularies? Hopefully things like Tao will address this, but it also seems like in the conversation earlier, somehow integrating the single object and multi-object communities will also go a long ways there. And finally, this also suggests that in this view of sort of streaming computation, some amount of forecasting is useful. And so that's something that maybe we've, as a community, sort of as a tracking community, has dipped their toe into in the context of sort of dynamic autoregressive models like Kalman filters. But it seems like there's also a rich space to think about where a lot of sort of innovative models can be explored. Okay, so I'll end there. Thanks.
Cool. Do you want to take a look at the questions? Maybe,
yes.
Yeah, maybe just a couple minutes and then.
Got it. Okay, so I see two. How important are physical models, DEQ, of motion in your approach? The work by Michael Jordan going in this direction in other fields of statistical ML. So I actually don't know what DEQ is, but I think, okay, so one place, if we were trying to guess what that was, is in the context of if I'm not able to see the data and I have to guess how the world is evolving, that's a natural place where I'm going to use physics to help sort of guess how the world is evolving if I can't see data. And so totally agreed that in some sense, a really good first order model would be a first order physics model. And so we're totally approximating that with just like 2D vectors of bounding box velocities and extrapolating there. So one concrete point is if we had 3D velocities, I would totally do that. And if we had more models that said how things would actually physically evolve, I think it would help us there. But the super crucial thing, at least from this computational story, was these things have to be lightweight. I found that to be sort of like, it's where this way of evaluation is sort of brutal in that you can come up with all these cool ideas, but unless it's actually fast, oftentimes it's better just to run your fancy, expensive single frame algorithm. So it'll be fun to see what happens. Okay, let's go on to the next question. Regarding biological inspiration for flow, I was also wondering how does that square with saccadic eye movements? Isn't that screwing up all sorts of long range motion info in humans and other primates? Okay, so this is how I would this is my interpretation of this question. So in fact, this work on sort of streaming processing, it started from our own exploration, not into any kind of different metric, but it was really, we want to think about attention. So essentially, I guess one, you can think about that as the manifestation of saccadic eye movements. Let's see, so I always think of when people are sort of perceiving so they can act in this world, there's usually too much information to deal with. And so we kind of almost do attentional processing, we focus on certain parts of it. So the hope is that we can use this kind of streaming evaluation framework to actually evaluate attentional processing as well. And when I say attentional processing, it's not sort of attention in the self-attention transformer view of things. This is sort of hard attention where I'm actually throwing away data. You could think about that's what this approach is already doing. It's throwing away frames just because I can't afford to compute on it. But you can kind of say, oh, maybe what I can do is I can look at a part of a frame if that's super cheap. And so that I think there's a world under which sort of attentional processing almost also emerges as a way of optimizing for streaming performance. Hopefully that answers Alyosha's question. Feel free to ask another one if it didn't.
Cool. Maybe, I think if that's all the questions, maybe we'll move on to the next talk. Especially given we're low on time.
Yes. Thanks.
All right. Thanks so much for the great talk. And we'll move on now to our last talk of the workshop. Thanks everyone for all the questions. That was a great discussion. So our last talk of this workshop is from Ross Girshick, who's a research scientist at Facebook AI Research. Ross has really been one of the driving forces behind progress in object detection. From work on RCNN, family of approaches, which basically formed the backbone of a lot of different research projects, as well as a lot of trackers, to his work on COCO and Elvis datasets. And as a result of this work, he was awarded the Pammy Young Researcher Award for Region Convolutional Networks and the Marr Prize at ICCV for Masked CNN. And at a high level, one of the motivations of this workshop was also to incorporate kind of lessons that have been learned in the broader recognition community into tracking. So I'm really excited to hear Ross's perspectives. One fun bit, Ross sent us this talk a few days ago, and I started listening to it, and I listened to 2 minutes, but it was really nice, so I stopped listening because I wanted to experience it for the first time in this workshop. So I hope you guys will enjoy it as well.
Thank you for inviting me to the Tracking and its Many Guises workshop at ECCV 2020, located here in lovely cyberspace. My name is Ross Girshick. I'm a research scientist at FAIR. I think my talk started out with the title, Lessons from the Detection Community. As I started to work on it, I realized that a lot of the lessons I might talk about look like things that the tracking community has already been doing, or perhaps just recently started doing. So I shifted gears a little bit and decided to put together several thoughts or perspectives that I've had floating around in my brain for a while, but never really put together into a presentation. I fear some of it may be painfully obvious, but I hope that enough of it will be a fresh perspective that you find it to be a useful way of looking at the type of work that we're all engaged in. So what is that work? What is it that we're all doing? Well, if you take a given area within computer vision, say tracking or object detection, at any given time, the researchers in this area are hammering away at some set of data sets and tasks. They're working hard on models and algorithms to optimize some evaluation metric. For some of these data sets, there will even be yearly challenges at which teams from all over the world will compete head-to-head to achieve the best result. If you look at this ecosystem at a snapshot in time, it looks like we're working on a fixed data set and optimizing some fixed task and metric. During this activity, it's easy to forget to ask the questions, why am I using this data set? Why am I addressing this task and not some other one? Why am I using this evaluation metric? And why are we competing in these challenges? The superficial answer to these questions is momentum. We work in this ecosystem simply because it's the one that exists. New data sets are really hard to build. They often take multiple years from start to end. They may be expensive. And if we're trying to do something new, for example, a new annotation task, then it may take significant experimentation before you find a successful implementation of the data collection process. Likewise, you work on tasks that already exist because there are already many baselines to compare with. Reviewers are familiar with what you're doing, so you don't need to convince them that it's important. And defining new tasks is also really hard. The same reasoning that applies to tasks also applies to the metrics that we use. So in a sense, at each moment in time, it feels very much like we're following the path of least resistance. But there's a different perspective that I think is far more optimistic, and I also think is better aligned with reality. But it requires taking a step back and considering not only what people are focused on right now, but instead looking at change over a longer arc of time. I think if we take this broader view, then we see that there is a lot of hard-won progress. That instead of fixed entities, datasets, tasks, and metrics and challenges are actually dynamic, and they have evolved significantly over time. Not only that, but algorithms and datasets are locked into coevolution with each other. Now, some people are arguing that the era of fixed datasets is dead. But I'd argue that it actually never existed in the first place, and that the dynamic nature of these things has actually been undervalued. So I want to apply the introduction that I just gave to 4 items: datasets, tasks, metrics, and challenges. And for each one, I want to give an informal case study of an important way in which this dynamic evolution has played out that moves our joint endeavor in a positive direction. These case studies come from my own experience as a researcher working mainly on detection and image recognition for more than 10 years now. Let's start with the first. Datasets are instruments. People typically think about models and algorithms first, and then datasets second. For example, how well does faster RCNN perform on datasets like Pascal VOC, COCO, or cityscapes? This is natural because we start by either writing or reading a paper about a specific algorithm, and then we see how it works on a few datasets or in a single dataset, possibly under different conditions. But you can also flip this perspective around. You can think of the dataset as a tool or an instrument that we use to measure how well a set of algorithms work. Different choices of dataset will define a different type of instrument that will allow you to learn different things about the set of algorithms. I think this perspective is crucial because we usually think of datasets as fixed, but this flip suggests that they are not fixed and that you can vary the dataset, and by doing so, something interesting might happen. If they are instruments, then we can build new ones that are better in any number of ways. I'm hinting at this by showing the icons progressing from a magnifying glass to a regular microscope and then to an electron microscope. Now there's a case study that I like to use for illustrating this perspective. It's image classification on MNIST, Pascal VOC, and ImageNet. I went to grad school in the pre-deep learning era. Hand-engineered features, SVMs, and convex optimization were the rage at that time. There are things that you've probably never heard about, like Fisher vectors, that were the cutting-edge feature representation. Winning a dataset challenge involved an ensemble, not of models, but of engineered feature representations such as Hog and SIFT, together with Fisher vectors and VLAD, and then training SVMs at an unprecedented scale. Of course, we all know that convolutional neural networks had been invented long before, and that in 2010, virtually no one in the computer vision community was using them. There are many reasons why, perhaps the lack of superfast GPU implementations, or a few missing ingredients, such as ReLU activations. But I would argue that the most fundamental reason is that we had not yet built the right instrument to differentiate between algorithms. Before ImageNet, ConvNets and SVMs gave similar results on MNIST and Pascal VOC classification. Now, given these empirical findings, the computer vision community had its own biases that made it prefer one of these methods versus the other. It's not until a new instrument was introduced that we could really see that ConvNets are actually more powerful than SVMs and Fisher vectors. ImageNet was that instrument. It was the first mainstream computer vision dataset that could really distinguish between these competing approaches. Of course, we all know what happened in 2012 with the breakthrough AlexNet result on ImageNet classification. The method proposed in that paper was significantly simpler than the existing SIFT plus Fisher vector state-of-the-art, but also gave much lower error rates. We can look into the detection community and observe a similar trend. Detection data sets have evolved over time. Probably the most important early one is Pascal VOC, which was originally prototyped back in 2005 in a much simpler form. Later, COCO was developed, and it made the images much more complex, added 4 times as many object categories, and greatly expanded the number of images. So the first point that I want to make is that datasets can be viewed as instruments. They let us measure how well algorithms are doing, but like any instrument, if they are too crude, then we cannot possibly reveal crucial differences between algorithms. As a result, we need to constantly develop new datasets that allow us to better measure how algorithms are working. Next, I want to look at tasks. Tasks are built on top of datasets, and they define the types of problems that the research community focuses on. Many of you have never seen an okapi before. Well, this is an okapi. I've given you one example, and I bet that if I show you a few more images, you'll do a pretty good job of saying whether or not they contain an okapi or not. Of course, there's a whole literature now devoted to this problem. It's called few-shot learning. I got interested in this area back in 2016 and was immediately struck by the fact that while the rest of computer vision was using challenging data sets, the few-shot literature at the time was working on omniglot or a miniaturized version of ImageNet called Mini-ImageNet. The evaluation protocol that was established made few-shot learning its own separate world. The assumption was that all that mattered was few-shot learning performance, and it was irrelevant how well the proposed classifier would work on categories with abundant data. This struck me as the wrong way to frame the problem. It was also against the notion of learning systems that are robust to the data abundant spectrum. Of course, a model and learning algorithm should work well when given little data, but it should also work well when given lots of data. It was difficult to understand if models and algorithms were in fact robust to data abundance because the research world was fractured into two camps. In Camp 1, in the upper left of this figure, which I'll call papers on the standard classification setup, you'd see results on standard data sets for which all classes have lots of training data. In Camp 2, the bottom right of this diagram, you'd see results on specially crafted few-shot classification data sets, in which you'd see accuracy for categories with few examples. These data sets were different, and the models and learning algorithms used for them were also different. It was impossible to compare and understand what was going on across these two camps. Now, what is the secret x-axis in this plot? You probably have a guess already, but I bet that you're wrong. What we found instead is that if you benchmark few-shot learning algorithms in a setting that measures accuracy on categories with many examples, as well as with few examples, there's typically a trade-off. Methods that were developed for few-shot learning were tuned in ways that actually hurt their performance when lots of data was available per class. On the flip side, tuning the algorithm to recover accuracy on the classes with many examples would then hurt accuracy on the classes with few examples. In general, you find a trade-off curve that looks like the one above. As an algorithm is tweaked to work better on few-shot learning, its performance when many examples are available drops. Bharath Hariharan and I developed and tried to promote a new benchmark that would test robustness to data abundance by measuring performance on classes that have lots of data, as well as classes that have very little data, in order to explicitly explore this trade-off. Of course, this diagram here is just a cartoon illustration of the observed trends. You can refer to the paper pointed to above for the actual experiments and data. Now, despite our best efforts, we were unable to persuade the few-shot learning community to adopt a robust evaluation perspective. And still, most few-shot learning evaluation is performed in this non-robust setting where one assumes that all classes have little data and performance when a lot of data is available is irrelevant. Now, to be fair, the setup that we proposed back in 2017 was overly complex, and the few-shot learning community already had significant momentum that we were trying to overcome. So we needed to offer something better. So I went back to the drawing board and hatched a scheme. The idea I schemed was to take an existing community that is passionate and cause them to work on few-shot learning even if it's not their primary concern. And the key to this plan is that few-shot learning is not some niche problem. It's fundamental to learning. Visual concepts are observed with different frequencies, and some things simply are rarely seen. So the rest of this case study will be about defining a new task for the object detection community that expands research in a very natural direction. That is, to recognize more object categories, and in doing so, will naturally cause researchers to work on few-shot learning and evaluate their methods in a robust setting. How this naturally happens all starts with the naming of things. Why do we want to name things? We name things in order to communicate. Obviously, this could be human-to-human communication. I ask for a wrench, and you know exactly what to hand me. But even more so in the future, it will be for human-to-machine communication. I ask my robot helper for a wrench, it looks at the environment around it, sees the wrench, and then hands it to me. If we expect automated systems to do many things in the world, they will need to have a vast vocabulary that can cover a wide range of situations. To illustrate this point, we can consider this image in more detail. In fact, we'll play a simple game. First, we'll mark an object in the image that's not already marked. Then we'll name it, and then we'll mark all the instances of it. And then, if there are no more unmarked objects, we're done. Otherwise, we'll repeat this. First, we see a car, because it's the largest, most salient object. Then, a wrench. We mark all the instances of the wrench. Then we see a bag, some bolts, an oil spray can, a car door handle, a cell phone, and so on. There are many things in this image, and we might ask an autonomous system about any of them. Our goal in the Elvis project was to provide a dataset and benchmark for research on this scenario. We want to take the field of object detection from the world of COCO with its 80 categories into the future, where detectors will be able to detect thousands of different object categories. That is, we want to support the task of detecting everything in an image. On the surface, this task might appear to be just about increasing the number of classes that a detector outputs. However, it exposes fundamental new research problems that I want to dig into in more detail: benchmarking and data-efficient learning. The benchmarking problem is all about how you define the detect everything task in a way that leads to tractable data annotation and fair evaluation. This is incredibly important because evaluation is how our community makes progress. For more insight into this, I recommend reading David Donahoe's 50 Years of Data Science and learning about the Common Task Framework. The second problem is about data-efficient learning. When a dataset contains a large number of categories, it will naturally contain frequently occurring categories, as well as a long tail of rarely occurring categories. And as we know, if categories have relatively few examples, accuracy of existing systems drops to very low levels. For example, if we reduce the COCO training data to 1,000 images, then AP, or average precision, for this particular detector drops from 36 to just 10. And this is a case in which 90% of the categories still have more than 20 examples, which might not even be considered low-shot learning by many people. Let's jump into problem 1, benchmarking. In order to make progress on the task of detecting everything, we need a suitable dataset for benchmarking. For that, we've introduced the Elvis Large Vocabulary Instance Segmentation dataset. We released a preview version of it at CVPR 2019, and I'm happy to announce that we released the final v1.0 release of Elvis back in June at CVPR 2020. Elvis now contains 160,000 annotated images, just over 1,200 categories that were discovered using the object spotting game that I showed you earlier, and just over 2 million instance segmentations. And due to the object spotting process, the dataset naturally contains a long-tailed distribution of object categories. I refer to this kind of data as big little data. It's big because it has a large number of annotated objects. In fact, it has 67% more annotated objects than COCO does. However, it's also little because there are a large number of categories that have relatively few training examples. Now, building Elvis is actually its own research challenge. Elvis is unlike previous detection datasets. I'll claim that Pascal and Coco were relatively easy to build in the sense that the data collection steps were pretty well understood. In particular, they started with a hand-selected set of categories that were chosen prior to image collection. Images were then collected by searching for these selected categories. This process means that categories can be well separated by design. There are few or no ambiguous cases. For example, no one will ever confuse a potted plant with a sofa. This design also means that annotating all instances of the small number of categories, a property that I'll refer to as exhaustive annotation, is easy to do. However, in Elvis, all of these nice properties go away. At the scale of thousands of object categories, the boundaries between categories can get fuzzy. Now, an NLP researcher once told me, the thing that computer vision people don't get is that the entity in the image is not the label. The label is just a referring expression. What this means is that for a given object or entity in an image, there are multiple valid ways to refer to it. That is, the category is a referring expression, and therefore an object may easily belong to multiple categories. For example, an object such as a toy deer may be referred to both as a toy and a deer. Cars and trucks are both vehicles, and backpack and rucksack are synonyms. If one were to try to build Elvis the same way that Coco was collected, it would require making more than 1,000 forced binary judgments for every object in every image. This is a non-starter because the volume of annotation work is too great, and the multiple referring expression issue will undoubtedly lead to many errors and inconsistencies in the annotations. The fact that we're dealing with referring expressions helps us understand a bit more deeply why object categories are fuzzy. It's fundamentally because people will disagree on how to refer to some things in the world. There are a lot of funny examples of this, such as an article in the Washington Post about the debate over if a hot dog is actually a taco or a sandwich. Or this article on Vice.com asking the eternal question of if cereal should be considered soup. While those might sound silly, a real example that I encountered is toast. It's easy to find bread that has been heated to a crisp and used in different contexts. So here on the left is something that I would consider very easily and clearly to be toast, probably because it's being served in the context of a breakfast. On the right, you also have bread that's been toasted to a crisp, but it's being used in a sandwich, so it doesn't feel like toast anymore. And then you have some examples in the middle, and here it becomes pretty unclear to me whether or not these should be considered toast. So we face many problems. How can we build a dataset that allows for multiple categories per object when facing the fact that exhaustive labeling is prohibitive with respect to both time and money? And additionally, exhaustive labeling does not necessarily make sense because many object categories are actually fuzzy. For example, the case of toast on the previous slide. But if we do not have exhaustive labels, is it even possible then to evaluate average precision of an object detector? And if we can't do that, then what's the purpose of the dataset? Amazingly, all of these problems are elegantly solved using a new way to structure object detection datasets that I call a federated dataset, which is not to be confused with federated learning. A federated dataset is a single dataset that is composed of the union of many smaller datasets. In this figure, the overall dataset D is shown as the union of smaller datasets, one for each category. Each category-specific dataset consists of positive images for that category and negative images for that category, indicated with the pluses and minuses. The same image may be shared between multiple per-category datasets. In fact, these per-category datasets heavily intersect each other in practice. This structure will provide sufficient conditions for computing average precision, which is the standard way that object detectors are evaluated. To see that, let's look at the guarantee provided for each category level dataset. So for category C, we have positive images in which all instances of category C are exhaustively labeled. And we also have negative images for which we guarantee that no instances of category C exist. Then there are all the other images in the dataset D. These images are unknown with respect to category C. The positive and negative sets are sufficient for computing AP for category C. During evaluation, the unknown images play no role in the evaluation for this category. Importantly, on the val and test sets, the positive, negative, and unknown membership is hidden, so the detector must assume that all images are labeled with all categories and try its best to output the objects that it thinks it's found. Federated dataset design has two nice properties that make building datasets like ELVIS tractable. First, because the category level positive and negative sets can be modest in size, this dramatically reduces the cost of labeling. Second, there is no forced choice when labeling objects. If an annotator cannot tell what label to apply to an object because it is on the fuzzy boundary between categories, then it can simply be left as unknown without creating a problem for evaluation. To collect this type of federated dataset, we used a custom 6-stage annotation process. It starts with the object spotting game I showed you earlier, in which objects are spotted in stage 1, and then all instances of spotted objects are labeled in stage 2. Then, in stages 3 and 4, we perform instance segmentation and quality verification, going back and forth until all instances have been segmented up to a certain level of quality. In the 5th stage, we check images to make sure that positive images are actually exhaustively annotated. If any case is found with missing annotations, for example, a missing book in this figure, then we flag that so it can be handled properly during evaluation. Finally, we collect a set of negative labeled images for each category. This process results in pairs of images and categories like these shown here. For example, this is an image that contains 2 beer kegs. They are not the most notable or salient objects in this scene, as you would typically find in many previous detection datasets. Another example, here are lanyards, like we would be wearing if ECCV were a physical meeting this year. And finally, one example to show off the quality of the segmentations that we've collected. We see the fine detail captured in the pineapple segmentations. So in summary, ELVIS is kind of a hack to focus research on the problem of few-shot learning. It builds on an active, fundamental research area, object detection, but it changes the problem in a way that will cause researchers to focus on algorithms that can generalize well from few examples, but can also work well in the case when many examples are available. So, to reiterate, tasks define the problems that the research community cares about. These problems should be aligned with bigger picture goals about what we, as a society, want to achieve. The last two will be much briefer, but I think they also offer important perspectives. Let's see how the choice of metrics can create differential rewards. For this, we will look at localization accuracy in the context of object detection. In object detection, the primary metric that is used is average precision. Average precision is essentially the area under the precision recall curve for a category. However, to compute this curve, it is necessary to grade each box or mask prediction as a true positive or false positive. This is generally done using a threshold on the intersection over union between a predicted object and its match in the ground truth. So let's look into intersection over union a bit more. There are two really nice illustrations, both from papers in 2014, that illustrate very intuitively what it means for boxes and masks to have a certain intersection over union overlap. You can see that for either boxes or masks, if you pick a low value, like 0.5, then the geometric objects can be fairly far apart from each other. Naturally, as the overlap requirement becomes higher, the entities start to align very well. When Pascal VOC was introduced, the choice at that time was to use IOU equals 0.5 as the single threshold at which to compute average precision. This means that the metric was only tuned to reward detections that are pretty loose. An algorithm would get no additional points for increasing the intersection over union of the objects it detects if nothing else about the system changed. When COCO was introduced, this decision was revisited. The explicit reasoning was that algorithms should be rewarded for providing better localization accuracy. But at the same time, if you just increase the threshold, it may not provide a continuous enough metric for gradual improvement. The solution, then, was to integrate over a range of intersection over union thresholds in order to provide a more continuous reward for better localization. This change repositions researchers to focus on a new world in which better localization accuracy is encouraged rather than just being ignored like it was before. So in summary, the choice of metrics can have a large impact on what people focus on within a given task. Selecting a metric usually has some kind of trade-off that will encourage work on one thing while possibly also discouraging work on something else. Finally, I want to briefly mention challenges. I've been part of challenges since 2008, either as a participant or more recently as an organizer. What we have seen consistently over the years is that challenge entries become very complex and usually involve constructing large ensembles of models. For years, we in the COCO committee had discussed if we should ban ensembles. And every year, we decided not to, because ensembles are hard to define, and therefore, we thought, would be hard to ban. This year, we did something different in the Elvis challenge. Rather than going through the same usual debate, we made a very quick decision to just go ahead and be bold and finally decide to ban ensembles. While ensembles are hard to define, we decided that most people would actually have a very reasonable sense of what to do. So we just decided to go ahead and try it out. This turned out to be a great decision. It had a very positive response. We actually received no questions of the form, is X an ensemble? And we got a lot of positive feedback about the choice as well. In particular, participants noted that by banning ensembles, we removed a huge logistic and computational burden, allowing them to focus more on the algorithmic contributions. My hope is that this can make challenges more inclusive and, for example, easier for smaller groups to enter. Second, I want to highlight the power of requiring a tech report at a challenge for each entry. Up until very recently, all that was required for a challenge entry was a very short description. Usually this was vague, contained no ablation studies, and therefore provided no insight. Also, this meant that the only way to invite teams for presentation was based on who had the best number. Now, both COCO and Elvis require a tech report for each entry, and it turns out this makes a huge difference. You often get a detailed description of what each team did, and detailed ablations of how much each design choice mattered. And critically, having this report allows you to give awards and talks based on much more than just who has the best number. For example, you can give an innovative method award. You can use this to reward a brave team that tried to do something different and quite likely might have put them in last place. That is, to take a simple baseline and show that one good idea can improve it by a lot. This generally can never win compared to method that might apply a dozen of improvements that have shown up in papers over the last few years, but it can still be a very solid contribution and make for a nice workshop talk. In summary, for challenges, we need to make them evolve over time and to establish new practices that can make them more effective at building a community around a dataset task and metric. To do this, we should have an eye towards changes that make them more inclusive by reducing computational demands and provide rewards for a more diverse set of entries. So I'd like to thank you for listening to my philosophical ramblings about these 4 topics. I sincerely hope that you found some of them to be new and refreshing and might help inform some of the decisions that you make in the future regarding any of the datasets, tasks, metrics, or challenges that you might be involved with.
All right. So thanks again to Ross for the excellent talk. Fortunately, due to a scheduling conflict, we couldn't actually have Ross with us, but feel free to ask questions and we'll answer them in the chat if we know the answers, or I'll try to pass them on to Ross later on. So with that said, I'll close off the workshop. I have a few slides and I'd like to thank some people. One sec. Not able to share my screen. Okay, there we go. All right, yeah, so thanks everyone for attending. I'd like to close off the workshop and thank a few people. So first of all, I'd like to thank the advising committee of the workshop for all their help. Deva Ramanan, Cordelia Schmid, Laura Leal-Taché, and Jordi Pontisset for all their help in questions that came up during the workshop, how to contact speakers, how to schedule things. They were super helpful. And of course, all the invited speakers for sending in talks or attending, and especially everyone who could make it to the roundtable. Thank you for a lively discussion. I won't read off all the names, but of course, thanks everyone. And special thanks to Patrick. Patrick was instrumental in actually setting up the Tau challenge this year. And without Patrick, we probably wouldn't have been able to have the challenge this year. So many thanks to Patrick. And to Scale AI, who helped us annotate the Tau data sets, particularly Adit Patel, Courtney Jung, and Nofel Nauman, who were on the team that helped us annotate this data. And to viewers like you. So thanks for attending, and we hope this this provided some useful discussion, and we hope we'll keep having workshops like this and assessing the state of tracking every year. So we look forward to seeing you at future conferences, hopefully live next time, but we'll see.